Please take a seat. Are you okay? Good.
Otherwise, you send a shockwave through the entire system. It's not good for it. Don't ever tap a mic. If you want to,
All right. Okay, good afternoon. We will get started. I hope everybody had a good lunch. As I mentioned at the end of the last session, we have a special guest, and since the lunch was distributed in terms of participants, we have asked our special guest to give a welcome remark. So it's my great pleasure to welcome Professor Susan Martinez. She's a Senior Vice Chancellor for Research and Innovation at the University of Illinois Urbana-Champaign. She's also the Stephen Sliger Professor of Molecular and Cellular Biology. So please give welcome to Susan. Thank you.
All right, thanks, Clara. And to those of you who think I'm going to speak 45 minutes, it was never going to be that. It's like 2 minutes. And we didn't want to disrupt all the energized voices at lunch. But it's just such a great pleasure to be here. When I passed through the food line and then I went outside to see everyone so engaged, lots of familiar faces, some people that have moved on and some I didn't know. It was just really, really fun. But it takes a birthday party like this to just pull everyone together, and that's really exciting. And this is a really exciting anniversary. When I think about what was happening 75 years ago, you know, the space race was just heating up. The polio vaccine was still a dream. The Korean War was raging, and the first coast-to-coast TV broadcast had just happened. It was against this backdrop that the Coordinated Science Lab was born. And I still remember, I've been in this position, I'm in my 9th year, and I can still remember that first few months, Clara and Normand came to my office. I'm a biochemist, so I didn't really know much about the coordinated science lab, and they wanted to make sure that I knew now that, there's a few campus interdisciplinary institutes that reported to me, and the Beckman Institute was put up when I was a graduate student here in '89, and there's nothing out here. So they wanted to make sure that I knew that CSL is the oldest interdisciplinary research unit on campus. So that was really clear. And they also talked about how CSL brought together researchers not only from computing, communications, control circuits, but also lots of other applications. So it was a really inspiring moment to me, and it's been great to be in this corner of campus and engage with these communities. I can't overemphasize enough how much this approach was, this sort of all-hands focus on an early seed that had really a profound influence on our university's reputation for interdisciplinary research, something that we think of as part of our DNA. While CSL is embedded in the Granger College of Engineering, its collaborations know no walls. It includes researchers from many other colleges, as well as our campus-wide research institutes that report into my office for the Vice Chancellor for Research and Innovation. Just some examples of what CSL has done and their center's researchers have worked on: robotics in healthcare with the College of Applied Health Sciences, computational genomics with the Carl Woese Institute for Genomic Biology, mathematics and decision control with the College of Liberal Arts and Sciences, the business aspect of technologies during COVID with Geese researchers, digital agriculture and food security with the Information Trust Institute and the College of ACES, and the legal issues of trust with the ITI as well. So, the CSL has clearly left a mark on campus and on our research community, and I'm just so proud of our just extraordinary history. And, there's still many problems to be solved, and as we think about the future and the many challenges that we face and the solutions society is seeking, it's not so different than in 1951. I'm really confident that the CSL will be front and center of research and innovation for many decades to come. So let me thank you for giving me just a couple minutes to speak on behalf of campus, and just want to wish you to enjoy the day. I'm sorry I can't stick around. I'll have to go off to something else, but just really it's a pleasure. So thank you very much, and enjoy the 75th. Thank you.
I think we will continue with our next session, and I would like to introduce Professor Veeravalli, who is the session chair for the next session.
Thank you, Clara. All right. So it gives me great pleasure to introduce Vince Poor, who's going to be our next speaker. Let me get this right. Vince Poor is currently the Michael Henry Strater University Professor at Princeton University. And he was also a dean for over 10 years, I believe, in the College of Engineering and Applied Science there. So Vince has made fundamental contributions to many, many different areas, starting with detection and estimation theory. And his textbook, I think many of us learned that topic from his famous textbook. But also in other areas like statistical signal processing, stochastic control, wireless communications, one of the pioneers of spread spectrum communications, made fundamental contribution to information theoretic security, and then more recently, power systems and machine learning. So he's won numerous awards for all his work, and if I were to list all of them, it'd probably take the whole hour. So, but I'm going to just point some of the highlights that he listed in his bio. So he's a member of the National Academy of Engineering, National Academy of Science. He's also a foreign member of the Royal Academy and many other national and international academies. And he's also received numerous IEEE awards, including the Alexander Graham Bell Medal and honorary doctorates from multiple universities around the world. But what I need to say is, so Vince started his academic career in at Illinois, in particular in the EC department at CSL, spent about 13 years, I believe. And he's remained a good friend of Illinois and CSL. So he's come back to campus numerous times to give invited lectures, participate in panels, participate in advisory committees. So thank you, Vince, for doing all of that for us over the years. And on a personal note, Vince was my thesis advisor, and he's remained a mentor, a collaborator, and friend, a good friend over the years. So thanks again, Vince, and join me in welcoming Vince to the stage.
Venu. Good afternoon, everyone, and thank you for that nice introduction, Venu. It's a real pleasure to be back in Urbana. It's an honor to have the opportunity to speak today. You know, I was here from 1977 to 1990, and you know, I really had a wonderful time here, both professionally and personally. My two daughters were born at Carl Hospital, and I have many friends here in Urbana, and some who've dispersed, but also made here in Urbana. And also professionally, this is a very nurturing environment. I think all the people here who've been fortunate to be faculty in CSL know how nurturing it is and how important it is to their careers. So when Clara asked me, invited me to give a talk here, of course I said yes immediately. And then I panicked because I had no idea what I was going to talk about. But then I realized that she gave me permission, actually, to talk about the past. Okay, so that's mainly what I'm going to talk about. I originally thought I'd talk about the past, present, and future of communications and signal processing in CSL, but we heard a lot this morning about the present and future, so I'm going to focus on what was happening at CSL back in the 1980s. Okay, and that was a time when the fundamentals for many of the things that we see today were being laid down, many of them in CSL. I keep saying in CSL, but of course it was over there, the corner of Goodwin and Springfield. And then I have this subtitle, The 80s Belong to Illini. Some of you who were here at that time know what that means, and those of you who don't, I will explain it momentarily. So when you saw this picture earlier in Clara's talk, so when I came to Urbana, this was where CSL was. It was over at the corner of Goodwin and Springfield, and CSL was 26 years old. I learned this morning that it is exactly 8 months and 1 day older than me. So I was still just 25, but then I quickly turned 26. So CSL and I are twins almost. It was what I found here was very strong established groups in some fields. So decision and control, which we're going to hear about tomorrow, circuits, which we're going to hear about later today, and physical electronics, which I don't know that's on this program, but we heard a lot about it, its influence on subsequent things that happened at Illinois. And then there were newer groups in communications, where I resided, signal processing and computer systems, which we heard about this morning. And then, you know, EE then as now was a very big department, about at least 100 faculty. So it was impossible to manage that in one centralized way. So it was decentralized. And the systems areas were primarily focused in CSL. And our sort of the boss of the systems area was Mac Van Valkenburg. I saw his picture briefly flashed up here. Mac later became Dean of Engineering here at Illinois. He was sort of the paterfamilias of all the systems areas, so decision and control, circuits, signal processing, and so forth. And he's really set the tone when I mentioned what a nurturing environment CSL was. He really set the tone. He was a great mentor. He made sure that we all had what we needed to succeed and that we were all recognized and our work was appreciated. So that was very important. He set the tone. All the other senior faculty were very similar to Mac in that way. They learned from him how to be good mentors. And then we heard about Joint Services Electronics Program. Bill mentioned it briefly this morning. And that was sort of the glue that held us all together. So it was a blanket contract grant, I'm not sure which one, joint services, so it was funded by Army, Navy, Air Force. And once a year, we all got funding from it, and once a year there was a review where people from the services came and we all talked about our research. So it was an opportunity for all of us to hear what each other was doing. So that, I think, helped promote that collaborative spirit that we heard about this morning. Just a note for the junior faculty that might be in the audience. When I came here, I mentioned the department was 100 strong. And the way that had come about is the then department head, a man named Ed Jordan, who was department head for 25 years, had grown the department by taking every position the university gave him and hiring 2 people. And he did that by putting people half on soft money. So all of us were half on soft money, or at least those of us in electrical engineering. And my soft money came from, I think, from JSAP. I'm not really sure. That was sort of transparent to me. So the day I arrived, I heard someone mention Pete Sauer this morning. Sadly, he's passed away a few years ago. So I arrived on the same day as Pete Sauer and Ken Jenkins, so another former CSL director. And getting ready for this talk, I talked to Ken a little bit about those days, and he reminded me about something that we did, and that was that when we first came, the job of the new assistant professors in CSL was to be the liquor chairs at the Allerton Conference. So the Allerton Conference is an important conference in the systems area. It's been run at Illinois for, 60, 70 years now. And it used to be held at the Allerton House. Now it's held in this building. And in those days, it was illegal to serve alcohol on state property. So the job of the junior faculty, or the new assistant professors, in this case it was me and Ken, was we were given a list and was sent over to the liquor store to buy everything on this list. And every afternoon we had to set up a bar at the Allerton House for everybody to have a happy hour and then take it down at night. And then afterwards, when Allerton was over, we took the unopened bottles back, and the remaining bottles, the ones that were already opened, we put in CSL. And there was drinking on state property, I think, because all that disappeared before the next Allerton conference. Anyway, I guess they weren't concerned about us being arrested for breaking the law. But anyway, we survived that, and I think today it's okay to have alcohol on state property. Anyway, this was CSL when I arrived. And the reason I have the subtitle was because the 1980s was a really exciting time in Urbana for sports fans. So I don't know, there's some gray hair out here, so there are people who remember this. But the mantra then was the 80s belonged to the Illini. And the 2 big money sports in those days, basketball and football, were both in the ascendancy here at Illinois. So in basketball, there was this coach, Lou Henson, maybe still the winningest basketball coach in Illinois history. And it was a very exciting time in basketball. The Illini went to many final NCAA tournaments. They made the Sweet 16 4 times. And just like this year, they made the Final Four. And just like this, that was 1989. And just like this year, they lost in the semis. But that year, they only lost by 2 points to Michigan in a buzzer beater. So it was a real heartbreaker. This year, I think they lost a lot worse than that. And in football, Illinois had hired this guy, Mike White, from the West Coast. He had been the head coach at Berkeley. And he brought in a West Coast-style football offense and brought in a lot of junior college transfers from California. And we had a really exciting football team. And one of the bellwether years was 1983, when Illinois beat every other team in the Big Ten. And that was the first time it had ever happened. And it was the last time it had ever happened, because now the Big Ten is the big whatever, 50 or whatever, and there's no way we're going to play round robin again. So, and this was a time, if you look here, 4 of those teams were rated in the top 20, and 3 were rated in the top 10, including Iowa, which was number 4, and Illinois beat Iowa 33-0. It was here in Urbana, so like a Champaign. Anyway, very, very exciting year. Anyway, the 80s belonged to the Illini. That was the mantra, and it really did in sports. But also it belonged to the Illini in other things, not only in sports, and particularly in research and CSL. So as I mentioned before, this was a time when the fundamentals of many fields were being laid down. And a lot of that was happening right here in CSL. And there were several groups, if you will, in the general area of communications and signal processing, tightly overlapping in some cases. And I'll just mention some of the people who were here during the 80s in these fields. So coding and information theory, which was a really strong area in Illinois at the time, probably maybe one of the strongest places in the field at that time. There were many people here, Erdal Erikan, Andrew Barron, both Tamer Bashar and Tangul Bashar, two Bashars. Although Tamer was in the decision and control group, he was also working in information theory. Dick Blayhut, whose name was mentioned earlier, Bruce, of course, who's still around. Bob McLeese, Mike Pursley, who sadly passed away recently, and Dilip Sarwadi, who's also in the audience today. And this was a really strong group. Just to give you an idea, 4 of them, these people, eventually received the Shannon Award, which is the top award in information theory. Erdal Erikan, Andrew Barron, Dick Blayhut, and Bob McLeese all later received the Shannon Awards. So it's a really high-power group in this field. Also in communication, and also you notice I have an asterisk there, and I mentioned at the bottom Dave Muller and Franco Preparata. So those are both, for those people in coding theory, those are very famous names. Reed-Muller codes, very well-known class of codes, invented, well, by Irv Reed, but also jointly with Dave Muller, and Franco Preparata, who's the inventor of Preparata codes. And the reason they're asterisked here is because although they had done these very notable things in coding theory, at this time, in the 80s, they were not working on coding theory. I think Franco was working on computational geometry at the time. I think that's right, Franco. Anyway, I'll say a little bit more about that later. Communications and networks. So, Tamer, this was the Tangul Bashar, actually, so it's a different Bashar. Bruce Hayek, of course, Bob McLeese, Mike Pursley again, and Dilip Sarwadi. In signal and image processing, there were 2 sort of distinct groups of people. Narendra Ahuja, who's here somewhere, I saw him at lunch. Bob Chen, who was then the director of CSL, and Tom Wong, who were working mainly on image analysis. And then Ken Jenkins, who I mentioned earlier, Doug Jones, and Dave Munson, so Dave's here somewhere too. And they were working more on digital signal processing and also on digital imaging. And I'm going to say more about all these people in a minute. And then finally, I want to mention AI and machine learning. There were, whatever is new is not really new. At the time, there was Dave Waltz was here. I didn't hear his name mentioned this morning. He was an early advocate of AI, and I'll say more about that later. And then Andrew Barron again and George Sabenko, both who were working on machine learning. So I'll talk more about that work later. I think I forgot the double asterisk under network, so I also mentioned Kumar. Kumar was here, but at that time he was working on adaptive control. He wasn't working on networks, but later he wrote a very, very important paper on scaling of wireless networks, which is very influential. So that's why he gets an asterisk and not something else. Anyway, so you should see there was a lot of people here. There were a lot of people here working in these fields. It was a very powerful environment. Now I'm just going to talk about some of the work that was being done. So in coding and information theory, so this was a time so information theory was born in the 1940s. So this is the 1980s, so it's already getting 35 years old at that time, roughly. And this was a time when people were pushing the boundaries and trying to understand what happens when you don't have good models and so forth. And that's a lot of the work that was being done was that type of work. So on the left is work by Mike Pursley and Bob McLeese and others looking at so-called universal source codes, which is a family of source codes that can achieve optimality for any source. So a source code is a compression algorithm like Limpel-Zib or something like that, or zip. And so there was a lot of interest in how do you do things when you don't know the model. So this is a little reminiscent of what's happening with machine learning these days. What do you do when you don't have a model? For my own interest, I was interested also in source coding, but more in lossy coding, rate distortion problem, also for situations where you don't know the model. what do you do? Also, Tamir and Tanguy were working on similar problems. Bruce was working on some very fundamental problems on information theory of stochastic processes. And I'm going to talk about Andrew's paper in a minute, but over there's a paper by Dillop. So Dillop is a coding theorist. He did a lot of work in this area, and I chose this paper to show because notice that the co-author is Arvind Krishna, who's going to be talking tomorrow. So this is when he was a pretty new student, I think, at the time. He later went on to work with Bruce. So I want to say a little bit about this paper by Andrew. This is a paper with Tom Cover, who was of Stanford, who had been his PhD advisor. So there was a lot of interest then, and in fact, there has been sort of consistently interest in the relationship, the importance of information in investing and in economics more generally. There was one of my colleagues at Princeton, Chris Sims, won a Nobel Prize for this about 10 years ago. And for this kind of work about 10 years ago. But at this time, so Tom Cover and Andrew were among the most prominent researchers in this area at the time. And this paper, I'm not sure if it ever influenced anyone's investing strategy, but it asked a very fundamental question, which is what is the value of side information when buying stock? And this kind of information was even, this kind of question was even explored by Claude Shannon in some of his work as well, and he claimed to have made a lot of money by applying information theory to the stock market. So what is the value of side information when buying stock? Well, within a certain pristine model, if you have a basket of stocks you're interested in, and you put their prices, for each trading period, you put their prices in a vector. You call that X1, X2, up to Xn. And then you have side information related to those prices, so Y1 up to Yn, and let delta be the increment in doubling rate in wealth due to the side information. Andrew and Tom showed that it's bounded by the mutual information between the stock vectors and the side information. So that's the best you can do. And then they also showed that this is an achievable bound. It can be achieved by a so-called horse race stock market where there's only one winner. Okay. Anyway, I don't know if this paper ever influenced anyone's investing strategies, but I thought it was an interesting thing. It's something I recalled from this time. So this is sort of one of the types of things that people were interested in the 1980s. In communications and networks, so this was very much a time when some things that are very familiar to us today were when the research was being done that sort of led to where we are today. And two of those things are this, cellular communications, and the internet. So there's a lot of what we do today. So this was sort of the dawn, really, of cellular communications. The first 1G came out in the 1980s, and it was a analog FM system. So anybody who remembers those days realizes it had fading and had all kinds of problems. It wasn't really that great. And so the industry had decided that 2G was going to be digital. So there was a big race on to figure out what was the right strategy for digital cellular. And so this whole idea of cellular communications and it becoming a major part of the telecommunications landscape drove a lot of research in the 80s. And for example, the idea of cellular communications in general, you have a base station and you have a lot of mobiles that are communicating to the base station. So it's a multiple access channel. So there was a lot of interest in trying to understand the properties and principles of multiple access communications. So for example, this paper by Bruce here looked at how do you control multi-access transmissions when they're all using the same radio resources. And this paper of mine, I was interested in detection. So that was my field at the time. And I was interested in how can you sort out a mix of a lot of different transmitted signals so that you can decode decode all of them accurately, okay, so-called multi-user detection. And this is one of the papers in that area. Another aspect of this was, as you heard, also Vanu mentioned was spread spectrum communication. So there was the so-called air interface, that is what kind of protocols were going to be used for multiple access, were being debated. And one of the prime candidates was spread spectrum. And I'm going to talk a little bit more about that later, but, or in a minute. But basically, there were sort of two types of spread spectrum that people were interested in here at Illinois in those days. One was so-called frequency hopping, and Mike Persley was sort of the main researcher in the field. He did some very influential work, particularly for some of the military radios that then started using spread spectrum, mostly frequency hopping. And then there's direct sequence spread spectrum. I'll talk about that again in a minute. But that was another very active research area here, was trying to sort through the kind of protocols that were going to be suitable for basically at that time 2G and further Gs, although we weren't sure how many Gs there were going to be, but at that time we were looking at just the first generation of digital cellular. This was also the time when the internet was being formed up, right? So people were very interested in networking protocols, how to routing protocols, flow control, and all these kind of problems. And Bruce was one of the pioneers in a lot of that area. And this is just one of his papers. There are many that I could have put up here. But this is a time when all the rules of the internet were being set up. So it was very influential work, very fundamental, but also very influential going forward. And then I mentioned Bob McLeese. I mean, he was mainly a coding theorist, but he also had worked at JPL on some of the deep space probe codes. So he's also interested in practical codes, and I just pulled out this one paper just to illustrate the sort of thing that he was doing, working on practical codes for photon channels. I'm going to talk a little bit more about this paper on the right here by Mike, Dillop, and Tangul. So this is oops, sorry, got ahead of myself there. Back up. Okay, so this is a very fundamental paper in spread spectrum communications. This and other work around it that was being done by this same group. So the way spread spectrum works, for those of you who don't know, is that it takes a relatively narrow band information signal and spreads it out over a much broader spectrum. And the original motivation for this was for covert communication, so you can spread the energy out far enough, it's below the noise, and an adversary can't then detect your communications. Okay, so it was invented in the 50s. Direct sequence spread spectrum is a technique that does this by taking a lower bandwidth digital communication signal and multiplying it by a very rapidly changing binary sequence, so-called spreading sequences. So this paper sort of was one of the first papers to look at what properties of those spreading sequences were most important for multiple access communication. So the same property that makes this covert, makes spread spectrum covert, also makes it useful for multiple access communications, because if you can put all your signals down at the noise level, and you know one spreading code out of many spreading codes, you can then pull your signal out of the noise, and the other signals just basically have very low impact on that process. So people were very interested in doing this. This was one of the proposals for digital cellular. And a lot of the basic properties of spreading codes that were important for using spread spectrum for multiple access were established in this paper. In particular, they looked very, very comprehensively at some fundamental cross-correlation and autocorrelation properties of spreading sequences, and determined what the ideal operating ranges were for direct sequence spread spectrum multiple access. Now, this work, it did turn out that spread spectrum became an air interface for cellular. It was one of the principal air interfaces for 3G, so-called code division multiple access, CDMA. And it also made it into the first Wi-Fi standard, 802.11b. Both cellular and Wi-Fi have since moved on to other air interfaces, but this was influential in some of the early days of these important technologies. So let me talk a little bit about signal and image processing, keep track of the time. So this was, as I mentioned, there were sort of two different groups here at Illinois and CSL in this area. One was Narendra Ahuja, Tom Wong, and Bob Chen. And they were working on basically some of the very fundamental early things having to do with extracting information from images. So edge detection. This is a paper by Bob Chen here in the middle on edge detection. Tom Wong, this student, I remember this very well. I was on this Steve Blostein's dissertation committee. This was a paper about detecting objects emerging in sequences of images. So I thought about this paper when I was watching Friday night, watching the landing or the arrival of the space capsule, thinking about these cameras looking up, looking for that thing coming, and trying to detect it as quickly as possible. And that's what this paper was about. This was in the days, if people remember Star Wars, when we were trying to build an anti-ballistic missile shield around the United States. And that really is what motivated that work in these days. You wanted to see those ICBMs as quickly as possible. But it's very relevant today with the kind of things that are happening today. This paper by Narendra, he did a tremendous amount of work on image modeling and image analysis, and this is a survey that he wrote in that area. There's also work here on digital beamforming, which is, of course, very efficient, very important in today's cellular systems and other wireless systems. I'm going to talk a little bit more about synthetic aperture radar, so I'll leave that till later. Again, I was interested in problems where the basic models no longer applied or could not be assumed to apply, so-called robustness problems. And this is something I've been working on a lot, and other people as well. And this is just a survey of some of the work. This is in 1985, some of the work in that area. Doug Jones arrived in Illinois late in the 80s. He had come from Rice, which was a sort of a hotbed of work in those days in digital signal processing. I can't remember, but it was particularly notable then. And he continued some of that work here. So I want to talk about this paper by Dave and Ken Jenkins. So this paper is about SAR. SAR, Clara told us that one of the early strengths of CSL was radar. And one of the things that was developed here at CSL in the early 50s was synthetic aperture radar. So synthetic aperture radar is a way of imaging the ground, getting a very high resolution image of the ground by using an airborne radar and flying by the area that you're trying to image, sending out pulses and collecting them, and then processing it all together to create an image. So what you basically do is you get a version of the two-dimensional Fourier transform of the area, and by inverting that, you can get an image of the area. So this paper, Ken and Dave had been working on computer-aided tomography. So this was a time when, medical imaging was being developed, really. So CAT scans in this instance. And they had developed some very efficient algorithms for that problem. So computer-aided tomography is very similar to SAR. And Ken and Dave noticed that. And they showed that they recognized first, and then they showed how it could be done, that SAR could be processed using the same principles as CAT scans. Okay, and by doing that, they were able to develop some very efficient algorithms using, for example, backpropagation with very high resolution, and then the earlier techniques were based on Doppler, and then naturally that extended to 3D. Okay, so this was a very influential paper. It's been cited many, many times. It's still referenced today. So I'll say a little bit more about this later. So another area of importance here was AI and machine learning. This is a smaller, at that time, smaller activity. Fewer people were working in this area. But I did want to mention Dave Waltz. So Dave Waltz, at that time, was a very prominent figure in AI. So AI today, we hear it every day. It's in every newspaper article and on everyone's lips all the time. but it's not new. AI goes back to at least the 50s, Marvin Minsky, MIT, and others. And it has had its ups and downs. And one of its ups was in the late 70s and early 80s. And Dave Waltz was one of the prominent people in this field, and he was in CSL. He wasn't in the communications group. I think he was in the computer systems group. But he was worked in natural language processing, and so he was like a public intellectual. So he wrote. I'm looking at his portfolio from that day. He had papers in all sorts of publications. This one was in Scientific American. So the general public was interested in AI even back then, and I thought this was kind of a neat paper. It was all non-technical basically, but it has the sort of prologue at the top here is. Computer programs not only play games, but also process visual information. Imagine that. They learn from experience and understand some natural language. The most challenging task is simulating common sense. So even then, they were debating the same things that we're debating now. Anyway, it's very, very influential at the time, but of course, artificial intelligence, probably because the technology wasn't there to realize it, sort of petered out for a while, and then it's taken off again, of course, in the present time. Machine learning, in the form of neural networks, of course, also is not new. It goes back probably to the 40s. But there have been various resurgences through the years, and of course now it's with deep learning and so forth, it's become ubiquitous. But for some reason that I don't know, there was a resurgence of interest in neural networks in the late 80s. And there were two people here, Andrew Barron, statistician, George Sabinko, applied mathematician, both in CSL, who were interested in putting down some fundamentals for neural networks. Andrew, actually I'm going to talk about him again in a second, but Andrew was trying to understand them from a statistical point of view. And George was trying to understand them as function approximators. What are the fundamental function approximating properties of neural networks? And I want to talk about that a little bit more here. So George asked the question, how well can an artificial neural network, what we just call neural networks now, approximate functions? And basically he showed that even a one-layer neural network with sigmoidal activation can approximate arbitrary classification functions with arbitrary accuracy on arbitrarily large subsets of an observation space. So basically confirming what people had thought, that neural networks can in fact approximate this kind of decision-making process. And of course we know that today very well, but in those days there has been a lot of doubt because in a previous era of interest in neural networks, Marvin Minsky had written a very pessimistic paper about neural networks and how well they would work. So this showed that in fact they would work well. And then I want to mention Andrew because it wasn't in this period, so I didn't include this paper, but about 5 years later, Andrew wrote another paper extending this, making much more applying to a much greater family of functions. And these two papers, this one by George and the one by Andrew, were very influential. These are sort of the first papers to show that neural networks can in fact be used to approximate fairly general functions, okay, which is what we use them for today. And I noticed, I was talking to Shrikant on one of my previous visits here, and he told me that then he was using these two papers together to make an argument for why neural networks are better. It's better for them to be deep than to be broad, and somehow this analysis played into that. So these papers were influential, at least at that time, and I assume since then. So that's all I want to talk about for those the 80s. But I do want to just mention some noteworthy pre-1980s classics. Because I came across them and I felt like I really needed to mention them. So Clara mentioned radar, and there was side-looking radar. SAR is also called side-looking radar. Side-looking radar was invented here. But I found this CSL technical report on the left, and I don't know if you can see it from the audience, but it's basically about pulsed radar. But the thing that caught my eye was the author. It's a guy named Peter Swerling. So anybody who knows about radar knows the name Peter Swerling. He's a very famous early radar pioneer, so apparently he was in CSL in the 50s, didn't know that. And if you do radar today, you model targets as swirling class 1, swirling class 2, swirling class 3, and so forth. So that's another very influential thing from CSL from that era. And then these other two papers are the coding papers I mentioned. The middle one is Franco's paper on nonlinear double error correcting codes, so-called preparata codes. It's before this period, which is why I didn't talk about it before, but I wanted to mention it. And the other one is Dave Muller's paper from 1952. This was in that journal that was mentioned, the IRE Transactions on Electronic Computers. This is really the paper that formed the basis of Reed-Muller codes, which is another famous class of codes. So anyway, there was a lot going on here. Mainly people were laying down fundamentals. That's what was really happening here. You didn't see a lot of pieces of equipment in my presentation. But what about now? Okay, so the focus of all this work was basically on building fundamentals for what were then emerging problems in communication, sensing, and learning. Okay, and so how does that relate to the present and future? Well, I think we heard already a lot this morning about communication, sensing, and learning, and all this relates to that. But I'll mention one thing in particular, and that's really my field, which is wireless networks. So a vision for next-gen wireless networks is the convergence of these things, convergence of communication, sensing, and learning. It really brings together many of the things that build on the works of the 1980s here at CSL. So source and channel coding, imaging and image analysis, radar sensing, wireless networking. So radar sensing, you saw the sensors on those cars this morning. Wireless networking, of course. Waveform design, designing waveforms that can accommodate communications and sensing at the same time. And AI and machine learning. So this all is what's coming together now in wireless networks of the future. And some of the potential applications, there are many. So situational awareness and sensing as a service. So things like localization and tracking, area imaging, which is what SAR does, drone monitoring and management. These are all potential applications, some of which are already happening. Smart home, so human activity detection for elder care. Spatial aware computing, that is helping people who are impaired use computing technology. So sensing is very important there, as is communication. Vehicular application, we heard about autonomous vehicles this morning. Of course, there's a lot of this in autonomous vehicles. They have a lot of radar, they have a lot of communications, and machine learning is important there. Driver assist systems and platooning. And then things like robot swarms, so smart manufacturing, environmental monitoring, and human-computer interaction in general. So there are a lot of potential applications where we bring all these technologies together. And again, a lot of the fundamentals were laid down right here in CSL or right over there on Goodwin and Springfield. So just an example, this one is maybe not the most prominent example, but I just want to point out that one problem of interest is using cellular system to image to also sense an image of the area that it's illuminating. And so in this problem, you have multiple base stations which illuminate some area, and they all collect backscatter, and then that backscatter can be centralized somewhere, and then you basically have a synthetic aperture, just like in synthetic aperture radar. So this is really the same problem that Dave and Ken were solving long ago, except that instead of having a plane fly by, you have multiple base stations out there collecting data. This is called ISAC, Integrated Sensing and Communication. So another example that brings it all together is extended reality, which has roles for ISAC, for basically machine learning of various types, generative AI to do smoothing and prediction, reinforcement learning, so Q learning to do resource allocation and handover and so forth. And this very, very high performance application brings together all these things in one technology. And again, all the fundamentals that were developed here have some role somewhere in this kind of application and many others. So I think I'm about out of time, so I'm going to stop there, and I'll just wish CSL happy birthday and say that the 80s belong to the Illini, and so does the future, and happy to take questions if we have time. Thank you. Ah, Yoram, yes, of course. Thank you. Sorry, Yoram. You know, I did it all from memory.
It was a long time ago.
Yes.
Yep.
I was afraid I was going to leave somebody out.
Vince, just as a footnote to Peter Swerling, you mentioned him. He's actually credited for developing Kalman filtering before Kalman. He has a 1959 paper which uses first-order systems like dynamical systems and using that as a signal model and coming up with recursive estimation.
Okay, another notch in your gun there, Clara. So. Okay. Okay, thank you. Sorry, Yoram.
Do you want me to leave space for the virtual guy?
We should go along to each other. Yeah, we should cluster. I think left is
Are you going to stand then?
no, I'll probably sit
Well, the idea was you would just be able to sit here. That way it's smoother, you know.
Thank you so much. Is this showing? Yeah. Do we have our participants on Zoom? Because we have 2 participants on Zoom.
Okay.
Yes. So we need to get them on Zoom.
Hey, Alan, can we do a mic test? Yes, can you hear me?
Yep, we hear you fine.
Yes, it's a bit
I
noisy.
hear you fine.
Okay.
It's
great.
noisy? Oh, okay. Hey, I have a question.
Go ahead.
I have a few slides I can show. Can I share?
Yes, let me
Won't
check.
take long. All you have to do is make it, shareable. Because I can hit share, but it says you have to do something.
Go ahead.
Okay.
Can you try sharing? Can you try sharing your
Yeah.
screen?
Sure. That worked.
Yes, it did work. Awesome. Thank
Okay.
you.
Okay, so I'll just show a few slides, because each of us says something, right?
Yes.
Okay.
Yes, exactly.
Okay, great. Okay,
So we
I
are
can
just
stop.
going to wait for a few minutes for Andy to join.
Yeah, I'll stop sharing for now.
Okay, thank you.
So Zoom puts things here, puts things there. So it's going to take us a few seconds to get things in order. Just be aware of that.
Yeah, no worries. I know Zoom can mess up everything.
He's the only, we don't have anybody else on the Zoom, so
Yeah, we are waiting for Professor Singer, so
I haven't heard anything from him.
can you text him? Sure.
Okay.
Yeah, I mean, we are a little bit early. If you can wait 2-3 more minutes for him. Great. Ah, here he is. Okay. Hey, Andy, can you hear us?
I can hear you.
Can you hear us?
Yes, I can hear you.
Great. If you can speak up just a little bit?
Hello, hello, hello.
Better. Do you have slides that you want to share?
Oh, I got this book. I'm going to read you this great book that I just got.
Okay, I agree.
We'll adjust the volume as we
Okay,
go.
sure, awesome. So I think the team is complete now. So welcome to the next panel session on communications and signal processing. And I would like to thank Vince for a fascinating review of the 1980s. And I'm very grateful you presented so much on coding theory. And our panel now has the next generation, and next gen meaning from the 1980s, and every bit as distinguished and accomplished. So our panelists are Professor Alan Bovik from University of Colorado Boulder, where I started my career many years ago.
Huh.
Yes. And I don't think that anyone on this list needs an introduction, but still I will go through some introductions. So Al got his PhD here at the University of Illinois. He worked with Tom Wong and Dave Munson. And he spent 41 years, I guess, at University of Texas, Austin before joining Colorado. And when I was reading his bio, my head was spinning from all the awards that I saw. So if you see someone winning awards that have the names Fourier and Gauss and mixed in between the Primetime Emmy Award, then you know exactly who are you talking to. And his work in image and video processing is one of a kind. So we are very happy to have you join us, Al, even if remotely. And our one award that I left out is the Edison medal, because I'm from Serbia. We believe Nikola Tesla deserves all the credit for everything. So I'm sorry I'm leaving that out. So the next speaker, the next panelist is Professor, or Madhow, if I can say so, who is also a graduate of Illinois, but he also spent quite some time visiting us, revisiting us, and spending time here as a professor as well. And he's a stellar contributor to the field of digital communication. He has many patents to his name. He is in the Inventors, let me call it Inventors Hall of Fame, and a distinguished lecturer of the IEEE Society. No? Oh, did I get that wrong? Okay, correction. That's why we need error correction, even nowadays. So, and then Muriel Médard, professor from MIT, who started her career here, and if I'm not wrong, you spent 2 years, hopefully no error correction needed there, before returning to MIT. Sorry? Roughly, okay. And Muriel received a large number of awards. She's a member of the National Academy of Engineering and I believe Sciences as well. Again, wrong, oh. But you got the Kobayashi Award and very recently the Hemming Medal, and special congratulations on that. And finally, a good friend and former colleague until very recently, Andy Singer, who is also joining us remotely. And Andy did some fundamental work on turbo equalization with our dear colleague Ralph Kötter, and then proceeded to build a great career in underwater communications. And one thing we all know Andy really well for is his entrepreneurial work. And here at Illinois, while he was here, he led the Center for Entrepreneurial Endeavors that involved a large number of students and faculty. And unfortunately, he's now at Stony Brook, and that's why he's joining us online. And after this error-prone introduction, I would like to get our panelists, distinguished panelists, to either present their slides, as Al will do, I'm assuming, or to share their thoughts about mostly CSL. If you read the titles of their presentations or talks or discussions, it's all about their experience at CSL. So once we finish that short trip down memory lane, we will take questions from the audience. And if he gets stuck at some point, I prepared a list of at least 20 questions, some of which were recommended by ChatGPT because I was running out of ideas. So let's see how that works. So we will go in alphabetical order. So Al, please feel free to share your slides and we'll take it from there.
Sure, happy to. By the way, I just want to mention that Nikola Tesla was also awarded the Edison Medal. So I feel very good company. Not rubbing it, he deserved it. And he also buried the hatchet with Edison at the presentation for it and said very gracious things. Anyway, I'm going to share some slides about my days at CSL, which were incredibly transformative for me. It's certainly where I grew up and where I became a researcher, and had amazing people that I met, both students, faculty, and everybody. First of all, I was advised by 2 CSL Hall of Famers who've been mentioned multiple times already. The incredible Dave Munson, who I couldn't believe it when I walked into his office and I said, hey, can I come work in this area? And he said, yes. And Tom Wong, who he later introduced me to. Dave went on to become president of Rensselaer Institute of Technology, which is an amazing accomplishment. He went that administrative path that I could never do. Tom, many people don't know it, but he was one of the inventors of video compression, one of the greatest engineering accomplishments ever, in my opinion. I also had the greatest teachers. And I'm just going to mention, I mean, there's many great teachers, but I want to mention two because from both of these individuals, I took at least 3 classes and maybe 4 from each of them. Every opportunity I saw them, teaching something new. Vince Poor and Bill Perkins were just remarkable. I've lost track of Bill, and I wish him well, but I'm pretty sure I took 4 classes from him in various areas of signal processing, systems theory, and control. An amazing teacher, and so is Vince. Back then, I worked on getting rid of noise from images. Today, all that work is completely irrelevant because machine learning has completely solved this problem very, very completely. But at the time, it seemed really tough. And here's, a picture from one of our articles and pictures of us 3 from that transactions on signal processing. One of the things we wondered about was, how good a job were we doing? There was no measurement of picture quality out there where we could say, oh, look, our way is better. A human would say that our, denoising result was better than anybody else's. And, so we couldn't prove it. And the only thing we could do is publish a picture like this, a grainy picture in the IEEE transactions. And that's what everybody had to base their opinions on. So at CSL, I had many teachers in communication theory and so on, and I learned that image processing was really a communication problem between the world and somebody capturing pictures of the world and somebody who's receiving those pictures of the world. And of course, in this picture, you can see that's manifested dramatically in a digital world of communications where communication channels are dominated by visual information because of companies like Netflix, Amazon, YouTube, it's basically streaming and social media and so on. Back then, we worked in the visual data channel space. Tom Wong with image compression, myself back then getting rid of noise and so on. But later on, I moved to consider other areas because distortion happens everywhere. And like any communication channel, the more that you understand about the transmitter and the receiver, the better job you can do. So when I finally took a job at Texas, I started to study the transmitter and the receiver. I started to work with companies like these companies to try to solve these problems, and I understood that there was really an infinite number of distortions that happen. We can't really model them mathematically. So the better thing to do was to try to, solve the problem in a different way. Tom Wong himself, the greatest image processor ever, in my opinion, stated that, in most applications, picture quality can only be defined in subjective terms. In other words, how people see them, and can only be measured in terms of observer response. Measurement of subjective image quality is very difficult. In other words, he's saying there were no algorithms for being able to accurately measure the quality of a picture as a human would report it. So the approach I took at Texas, I started to interact with neuroscientists and visual psychologists, and I sort of self-trained in those areas. And I learned, we can model the visual brain in many ways that might be effective for this problem. In other words, along the visual pathway. And I also learned that the world itself obeys rigorous statistical laws. Pictures of the world and videos are actually very regular. It's really principles of statistical physics. And you put these two together and you find these dual mathematical models that can be used to, predict picture quality. All along the pathway from the retina to the midbrain to the back of the brain where primary visual cortex resides. Applications of this are everywhere, but one of the biggest is in controlling compression. Everybody compresses videos, otherwise we'd have no video communication. Thanks to Tom Wong's work on compression early on, the MPEG standards now make it possible, and digital video traffic is basically 70% of internet traffic. Thanks to Tom and people who followed Tom and who worked with Tom at the time, like Arun Netravalli. Our work in Texas, we've been very proud of and following in Tom's tracks, is to use neuroscience to create video quality predictors that control compression. make it so that a streamer like Netflix can push the compression as far as possible in such a way that humans won't see the distortions. And we've been lucky enough to get a couple of Emmy Awards for this. And I just, I wish Tom was still here. I miss him so much. But Dave is here, and well, 2 of your grandkids got to carry these Emmy statuettes. And this all became possible because of my training from the greatest people at the University of Illinois in the Coordinated Science Lab. And so that's all I have to say about that. I will stop sharing and come back.
Thank you so much. I think we're going in alphabetical order, so our next presenter is, or discussant is Madhow.
Okay.
Please go ahead.
All right. Okay, so I don't have slides. So I'm a CSL two-timer, right? I was a grad student here from 85 to 90, and then as I was trying to figure out what to do with my life, they gave me a chance of being a visiting faculty here, and I had to teach for that, and I had to torture my fellow. They wouldn't unleash me on undergrads, so I taught 2 grad classes right after my PhD. So that was quite interesting way to form myself. I'll tell you more about the grad student days. And then I went away for 3 years to something that is no longer exists, Bell Communications Research, and there I sort of got training, kind of blue sky industry research, kind of like a Bell Labs ethos. And then I was honored to be invited back here as a faculty member, and I stayed on here until end of '99, and then moved to California. So that's a short history, but let me get into more of the details of how it actually influenced me. So so we've heard a lot about the large projects and things like that, and we had the JSEP umbrella that was still there when I was a grad student. So what that did for at least those of us in the communication group is it gave us a lot of freedom of just, Mike Persley, who was my advisor, he's passed away sadly last year, he basically gave me complete freedom on thinking about the PhD topic. And I made a mess of it, but it was my mess. So I went away and thought about it. He handed me some problem on universal receivers. I did something. It never went anywhere. I got my PhD out of it. But I got to own it completely. And that was a real privilege. And it's something that, influenced me throughout afterwards. Basically, you can think from scratch about some concept system and come up with ideas for it. And if you choose it right, those ideas can make an impact. The other part of the experience was being able to walk into any office of, especially Bruce's office. I would bug him a lot, and it would be open, and that's very, very unusual as well. A third part that was different was also we were encouraged to take math classes and just graduate math classes, just go do your thing. And I got really sucked into that. And again, this is stuff that I never used explicitly, but again, it was part of a very critical part of my formation. And I think I'm going to perhaps get to it. This kind of thing, I think, is even more important as AI pervades our lives. But okay. So Bell Core, I learned basically to brainstorm with colleagues and think about systems that are vaguely related to reality. Again, it was blue sky research. We weren't necessarily trying to do something useful, but a couple of really interesting things that influenced my later work came out of it. TCP/IP, interference suppression, such like. And so when I came back to Illinois, I was roped in right away into, again, talking about the collegial environment and the way people take care of you. I was roped in right away into this big proposal that Bruce and others were putting together for the Army. So I came in, I guess we came here June or something like that. I was writing the proposal over the summer, kind of racing to finish my contributions by the time my first child, Sylvia, was being born in August. So that was sort of the entry into Illinois faculty life. And of course, a great part of it, of course, was that we would always go out for lunch on Wednesdays, and I would get to argue politics with Dick Blahat, and it would get red in the face. It was really awesome, pretty awesome. That was the best part of lunch, actually. needling Dick.
Are you still arguing with him, or?
No. At one point, Dilip took me aside and said that you're just, did you see his face? He was getting too red. So yeah, so I kind of toned back after that. But it was basically, the collegialities and really the freedom to think and the space and time to think is really important. And so I think they had asked me for a title, and I said classical comm/SP in the age of AI and et cetera, something like that. So I think, okay, so right now what's happening is, we are all super impressed with AI, right? We have to be. It's just like the jump that has happened over the past year is just ridiculous, right? It's really a brainstorming colleague. It does your code for you. It's just amazing. There's no doubt about it. So people who are well-formed, I think they can really use AI in a very productive way. I think we are at that point that we can do that. I am terrified of people who are not quite formed yet, people who are in high school, people who are in entering college, and just counting on these tools to help them out. And in that context, I'm going to start with the education part first. In that context, I think things like signal systems, probability, those kinds of things are apart from so I think we have two parts of humanity. One is our intellect, and the other is our emotions. We are engineers, we won't talk about the emotions part. But for the intellectual part, the kind of, in some sense, being human means being able to handle logic and math and things like that. The kind of things that we do in communication and signal processing has to be, I think, part of education. Now, how you morph it, I don't know, but certainly just saying, go get this done with AI tools means we will lose an essential part of our humanity. And then when things really start blowing up in our faces, we won't know how to react. So I think in that sense, it's a really important part. The other part is that even in terms of research, I see this thing of everybody's asking, are you using AI? And again, obviously, there are many places where you must use it and to really make progress. But there are also places where classical methods work well. And again, I'm worried that without judgment that is built up based on some amount of using your own brain, we are going to be in trouble. And the way this connects back to my CSL time really is that I was just given time to think. And I don't know whether we are able to do that. We think we have the luxury of giving it to our grad students or not. I hope in a place like CSL, it is possible still. But the pressures are immense generally. I see my younger colleagues, the pressures they feel are immense. And I would like to advocate for at least some retro approach to graduate school and research in addition to getting things done that we have locked into. So I'm going to stop with that for now and let next person.
Thank you very much, Madhow. Next, Muriel.
Yes, so I arrived here in '98. This was my first academic job. I had done my PhD at MIT, all my undergraduate degrees at MIT, and then I had gone to MIT Lincoln Lab, and I was working there as a member of technical staff. And I think we've heard a lot about the collegiality and the space to think. I think what really struck me coming here is that really people believed in you. I remember starting at the same time as Andy as our dear colleague Ralph Coder, whom he mentioned. And I remember Ralph and I spending many hours walking around. He was trying to quit smoking. And I was walking because I was so pregnant and my ankles were getting swollen. And so we would kind of go walking around and do walking discussions. And we were both wondering, why did they hire us? You had this, but the point is, we were wondering, but it looked like the people around us were not wondering. And I came in with a sort of an unusual background. I had done my doctorate with Bob Gallagher at MIT in information theory of wireless networks. And then when I graduated, wireless was all the hottest thing. So, of course, I took the only job that I was offered that had nothing to do with wireless. And I went to work in optical network security. And so I came with this very unusual background with like two different things that seemed to have nothing to do with each other. And, rather than tell me, that's just weird, Muriel, it's like, oh, that's really interesting. You could really look at something, maybe joining those two different topics. And as Ralph and I were walking around, I think it was Bruce who sort of noticed that we were just wandering around aimlessly. And, sort of called in this two junior faculty who were trying not to bump into things. And he said, oh, have you looked at this recent paper on network coding? And, of course, Ralph was very much a coding person. Of course, had done coding as an information theorist, but at the time was doing networking, particularly network reliability. And, it was one of those epiphanies where we started saying, oh, could you actually try to express, for instance, what networks do to respond to disaster as a code? And that's what got us going with algebraic network coding. And, right now, I'm taken a leave of absence to form a company named Optimum, which actually does network coding for blockchain. But, I can trace all of that absolutely to being here and to be given that space to explore not just the space, but the encouragement, the intellectual nudge. I think another thing that was very formative for me was we've heard a lot about the collegiality. I was actually very torn about starting an academic career. I'd had my first child in grad school. And when I came here, I was pregnant with my second. And there was just such a welcoming, really friendly environment. I mean, I remember, on Wednesdays, sometimes we would take turns taking care of each other's kids, with Madhow and sometimes with Shrikant and that sort of, I don't know, co-op of babysitting. I don't know where else you would get that, and then so one Wednesday out of 3 you were taking care of everybody's kids, but then 2 Wednesdays out of 3 you were writing proposals, and it was just, and of course the kids loved it. As far as they were concerned, it was a party every Wednesday. So that sort of combination of very friendly environment, of people really believing in you, and then of people being supportive of you and also pointing you towards things. And of course, we talked about funding. I also remember, Bruce putting me on a proposal. I think I wrote something. I'm sure it wasn't very good. I hadn't really done proposals, but he's like, yeah, that's great. And so I'm sure I rewrote it and put it in. But it was that sort of combination of exploration and also having these amazing colleagues. And of course, so many people were like, oh, I want to work with you. Shrikant, Madhow, Sean Mine. So many people basically said, oh, let's work together. It was so validating, and from having that level of external confidence in you, that what you were doing was interesting, and even if it was quirky because it was novel. It really set me up. It really set me up for success. And, I don't think I would have survived at MIT if I hadn't come here. I mean, of course, one cannot do counterfactual, but it really set me up. And actually, one of the things that I'd like to mention, so, I mentioned my advisor for my doctoral advisor was Bob Gallagher. And when I was thinking of where to go, I had a few offers. I said, well, what do you think, Bob? And he said, Illinois is the best place for comms. Like, okay, all right, just go there. Like, gotcha. So yes, it's, I don't know what the title I gave at the end was, but my first title, and I'm sticking with it even if I gave a different title because I was told that my title was too generic. My original title is How CSL Set Me Up for Success. And then that is the title. Okay, I stuck to my guns. I was like, no, that's actually what I want to talk about. So that's my title, and I'm sticking to it.
Thank you so much, Muriel. And now we're turning to Zoom again. Andy, the podium is yours, or the Zoom link is yours?
Zoom, can you hear me?
Yes.
Fantastic. Well, I wish I was there with all of you. It's great to see you, Muriel and Madhow. It's been a while. So thanks for inviting me and for letting me be a part of this panel. It's 75 years is a long time. And thinking back, I spent 25 of those 75 years at CSL. So it's I guess 1/3 of the CSL history is also my history, which is why I feel such a strong connection. I'll start with a confession. I almost stayed at Illinois forever. I was almost a lifer, and it's not because I didn't have any ambition to go anywhere else. And I think that in general, people stay at Illinois because it's such a great place to be, and it's so natural. There's so much going on all the time, so many new opportunities, and I think people just sort of get pulled away to great opportunities, and they still don't know, whether they should have left, what they had that was so great. So as you said, I took the opportunity to become Dean of Engineering at Stony Brook, and the decision was hard. But CSL continues to shape sort of how I think about research, how I think about institutions, and what it means to build something that lasts. So when I arrived at CSL back in 1998, there was a remarkable group of young faculty who had just joined at the same time. Ralph was there, of course, Steve Lametta, Jen Bernhardt, Muriel, and then many others, not only within ECE, but across CSL and the campus. And there was a vibrant, young, energetic sort of group of faculty. But the thing that really drew me to Illinois in the first place was when we came to visit, at least when I came to visit, the senior faculty were really, truly interested in what we were doing and what we wanted to do and the problems we wanted to work on. And they got along with each other and they collaborated. And it was just, Muriel and I were both at MIT together, undergrad and grad. And, there were more silos at MIT, and there was less of the people sitting outside and, talking about a proposal they're going to write together, at least back in the 80s and 90s. Just down the hall for me, Bruce Hayek, Dave Munson, Tamara Bouchard, Gorham Bresler, Ken Jenkins, Doug Jones, Dilip Sarwati. These are great, all-time greats of CSL, and their doors were open, and they were collaborating and excited to work with you on a problem or a proposal or anything, or invite you over for a barbecue. And that culture, sort of welcoming senior faculty, really investing in junior faculty, resources that were shared and not hoarded. That was by design. It was CSL's sort of defining feature. I remember when I first got started, Dave Munson was, he helped me negotiate my startup package. And if there's any junior faculty in the room, the startup packages that we got back in the 1990s were, I think, about 5% of what we're giving to faculty now. So Dave told me that I needed to put my startup package towards the computing resources for the signal processing group. And I said, okay, because I assumed that that was what you did, and I didn't hesitate. And it wasn't because I was generous. It was just I understood that this was how CSL worked, and it benefited everyone rather than each of us trying to sort of build our own little mini systems. And that welcome went beyond research. Dave and Nancy Munson were so warm and friendly. When our daughter was born, the first people outside our family that we trusted to look after Elizabeth were Dave and Nancy and their boys. And that's a community. That's what CSL was. Growing up, in that community, I'm not going to talk about Ralph because I can't. So I'll move on to Mark Hasegawa Johnson. Mark was an affiliate member of CSL and also a fellow MIT alum. And he and I shared so much of our background together at Illinois, having both been, undergrads and grad students together at MIT. But then, at Illinois, our wives had been at MIT together and were undergrads as well. Our kids grew up together. And it just, you not only felt like you were connected as colleagues with people in the department, but you feel like you're part of a family. And then there were triathlons. There was a time period when, I think when my wife was pregnant with the first child, I put on 2 pounds for every 1 pound that she put on. So then Ralph and I had a bet to see who could lose more weight.
I remember this.
Yeah. He had quit smoking and started eating, and I had just started eating. So I started losing some weight and started doing a little jogging, and then did the Champaign mini triathlon. And then I met some people in town that did Ironman races and started doing some of those. And Bruce Hyatt kept telling me about how great of a runner he used to be. And back in the day, he could run a sub 3-hour marathon, and boy, was he in shape, but he was never running. So I finally just goaded him into, if you can run, well, why can you swim? Can you ride a bike? Why don't you show up and do a race? So I convinced him to do a half Ironman, and he did amazing. And he joined me in the next one that I did. And then I got Brian Lilly from the Technology Entrepreneur Center, who rode a bike to work in sandals every day, and got him to join as well. And before long, we were doing races together, and we were cheering each other off the finish line late at night because none of us were fast. And then Mindo joined the ranks, and it was a great community of colleagues that we not only collaborated with on proposals, but we also went out and training rides and traveled to races to suffer together. So it was an all-around community at CSL that was just so much fun. You mentioned entrepreneurship. That's another sort of piece that grew out of my time at CSL. When I first joined, the dot-com era was kind of upon us. I think one of Muriel and my colleagues from the MIT Lincoln Lab days had just, sold their company for hundreds of millions of dollars, and everyone around the country was digging into communication systems and starting entities. So Naresh Shanbag and I were trying to figure out, well, what could we do linking our commercial activity to our commercial experience to things we're doing at the university. And that led to us starting intersymbol communications. And it was around the time that entrepreneurship was sort of just starting to take hold at Illinois. They stopped chasing people off campus for starting companies and kind of tolerated us. But it was an interesting time. There were a number of faculty in the college and even in CSL that were starting businesses around that time. And intersymbol eventually got sold to a company out west, and the design team, chip design team, is still there on Fox Drive. Shortly after that, I was asked to take over the Technology Entrepreneur Center as director, and help it move from a general engineering department entity into something at the college level. And one of the things that I saw as sort of a necessary component to that was, well, we need to be able to leverage the great ecosystem that is CSL in order to make that happen. So we brought the TEC over into the CSL building, and it really, I think, benefited the students and faculty that were involved in the TEC, but also benefited the students and faculty at CSL as well. And, over time, I started another company with a CSL graduate student of mine, Thomas Riedel, who was interested in coding theory, but he was even more interested in building something from nothing. And that led to a company called OceanCom that makes use of the underwater acoustic communications that we developed at CSL. Over time, TEC flourished, CSL flourished. There were many interactions that led to growth of what TEC could do, and the ILEE degree program sort of launched out of that. The Chicago City Scholars Program launched out of that. And Illinois in general, and the TEC and CSL in particular, are sort of seen nationally as a true leading group when it comes to innovating and spinning research-based entities out of universities. As part of that, on the research side, Naresh and I had sort of developed this notion of signal processing being used to rescue the semiconductor industry from the end of Moore's Law. We wrote a proposal to NSF called Signal Processing to the Rescue of Moore's Law, and they funded it, and then DARPA funded that idea, and then that led to even more interest in this notion of building processing and communication fabrics out of devices that were operating beyond their natural capabilities, and that led to the Sonic Center, Systems on Nanoscale Information Fabrics. It was also a tremendous success led through CSL from Naresh and many of the faculty in CSL participating. I think we had more than 25 faculty from across the United States and 100 PhD students and postdocs. It really had sort of CSL thinking at a national scale. As that wound down, and by a couple of years ago, 2023, my kids had grown up and moved on from Champaign. My wife had retired after a long career, ending as a senior VP at Yahoo in the research park. And an opportunity arose to become a dean of engineering at Stony Brook. It's a AAU research institution. It's a public flagship. It has 40% of its undergraduate students are first generation. More than 40% of them are Pell eligible. And I asked myself, something that probably many of you have also asked, and I know that Muriel and Madhow have for sure, whether you could stay at a place that's extraordinarily good to you, or maybe take some of that CSL magic and bring it somewhere else that other people could benefit from it. And ultimately, that's what I chose to do. And I moved on. And remarkably, there's such a tight-knit group of CSL alumni that are out there. We were just at Bill Sanders' inauguration at RIT, and together there was Dave Munson, Bill Sanders, Ken Fox, Andreas Gangalaris, and many others, all of whom had moved on to administrative positions elsewhere in the country and around the world. Adi was there from Kazakhstan, although I think he's moved back to Texas now. So CSL really has worked itself into the broader landscape of higher education. And I think as Al pointed out earlier, Bill was the newest president of RIT, replacing who else? Dave Munson. And it became clear that CSL really taught people how to be good citizens, how to be administrators, how to build and grow research and educational institutions that work well. So, when I face a difficult institutional challenge here at Stony Brook, I find myself all the time asking, what would we have done at Illinois? How would we have approached this at CSL? And, how would the shared governance mechanisms that we put into place there work where we are here? And that usually is a guide to something that will work well. I still have 3 grad students at CSL, so I'm not done yet. And the research that I'm most excited about, right now are evolutions of classical signal processing and modern machine learning. And I think there's always opportunities going on at CSL. It's a place where that kind of thinking can continue to flourish. I'm proud to have been part of the last 75 years at CSL, and I'm pretty confident that some of the best chapters are still ahead.
Thank you, Andy. Thank you. And thank you again to all panelists. So in the spirit of democracy, I would like to open the podium to the audience for questions. And if you have a question that is specifically targeting one of our panel members, please say so. Otherwise, I'll obviously, I mentioned democracy, we'll let everyone say what their opinion is about the question. Anyone? Yes?
I just want to tell Andy that he can't hear you.
Oh, you need a microphone, right?
Just want to tell Andy that when I started here, my startup package was 0. So,
So it could have been worse.
as a former dean, I feel your pain with the hiring these days and startup packages. So. It was actually less than 0. I brought an NSF grant with me to Illinois. So.
So any other questions? Okay, that's why I asked ChatGPT. Give me a large number of really interesting questions. I will start with the comment that Andy made, and it's also in his biography here. It says, Singer still advises 3 graduate students at CSL, and both Al and Madhow were students here. And I would like to know what kind of advice would you give to our students? Because I've seen in the audience mostly faculty and visitors, but there are little pockets of our brilliant students scattered around. And I think our biggest treasure, at least in my opinion, always were our students. You see how well our students did, both in academia and in terms of creating new companies, starting new research directions. So what would be your advice to our current students? And I think you might have touched upon that topic a little bit as well, in terms of what kind of careers, what kind of visions should they have for signal processing and communication in the nowadays when everything is really dominated by AI-centric research. And what would you try to share as your wisdom from one generation of CSL and EC students, or broaden it up, CSL, let's say, to 2 generations or 3 generations down the road?
You asking me first?
Yes.
Okay.
Yes. I'll start with our 2 alumni, you and then Andy.
Okay. Al, right?
Oh, sorry, Al.
Oh, me. Okay.
Thank you.
Yes, sure. Well,
yes,
the kind.
go alphabetically. My bad. Sure, go ahead.
Okay. Can you hear me? Okay. Yeah. Okay. So what I always tell students, and you find that it's not always true, is first of all, are they pursuing something that they are really fascinated by and really interested in? Because you're training for a job you're going to have the rest of your life, and if you're not really into it because you're a fanatic, okay, then it's probably not the right field. And a lot of people do go to school and grad school and everything for reasons other than that, family pressure and that sort of thing. At Illinois, aside from spend as much time on the quad as you can playing frisbee, going to Garcia's and Papadels, and live close to campus because you can, and it's a beautiful place. This world now, Vince made an understatement a little while ago that, deep learning is ubiquitous. It's like our economy now. And, it's kind of a scary thing for a lot of graduates because they're having a harder time finding jobs and so on in this environment, especially if they're, computer science or they're viewed as programming and that kind of thing. And in that environment, what do you do, especially if you're, fairly along in your career? Well, one thing is, remember, it's also data science, and I try to tell students become expert at, data collection as well, because this isn't something that machine learning models are very good at, is, going and collecting real data in some branch of science or application or something like that. So, if you can steer things that direction, it's probably great job insurance. And I'm finding that my students who, they conduct big human studies, they're very much in demand still and all getting jobs. So I can speak from experience in that direction. And gee, don't take pride in your programming because the machines are getting better. And don't hinge your career on that. The programming interview is going away pretty soon, and it's just going to be different. So try to learn as much as you can holistically about this field of deep learning, because it's constantly evolving and changing in new directions that are unexpected. And don't take you take it very seriously, but these machines are not intelligent. They're not really, despite claims of AGI and so on by a number of industry pontiffs. It's not really true. They're just very good at organizing and retrieving data and put it together in a language type sense. So believe in yourself and don't get intimidated in this environment either, because human ingenuity is really behind all advances still. I'm not hearing anybody saying, well, machines are doing anything alone too much. Hasibi, or I forget his last name, the fellow who won the Nobel, the protein folding, that was their brilliance that guided these machines to solve the protein folding problem, for example. And so following that kind of path where you're thinking for yourself and trying to be as creative as possible as you use these new tools. There's always new tools that seem, like they're going to change everything, like the calculator at one point in time. I hate to use that example again, but it's the only one that came to mind. So yeah, enjoy your academic career most of all. I certainly enjoyed it with my two very relaxed advisors. Going to see Dave was kind of a weekly thing, talking with him about everything, not just about research and so on, but just about stuff. And he was always very relaxed. And seeing Tom was always a wonderful visit that was a little more intense because he asked, questions that were hard every time I would go see him, but everything was very relaxed too. And I, enjoyed my time there, and be sure that you enjoy yours. You only get to be in grad school once and in college once. That's all.
Thank you all.
So I'll start with the last thing that Al said, which is to definitely enjoy your time. And in fact, that's something I wanted to say in my follow-up remarks. So one thing that made my time enjoyable here was also a group of friends that we had, with Shrikant and Arvind and Swami. There were a bunch of people, I guess it's just a bunch of Indians that came in from the IITs and hanging out together. And also some white guys too, Colin, and yeah. So we had a nice bunch of friends, and it's really good to have that and to cherish that as you go along. And I think it's even more important to do that in the age of AI, right? Again, as I said, there's only two things here, which is in terms of there's the emotional part and the interpersonal part, and then the technical part, right, of intellectual part of being a human. So the friends part is super important, I think, and this is going to be the start of your network, right? Don't think of it that way, but I mean that's what it is. And then actually getting down into the depths of math and physics, I think are going to be important, because in order to even think of whether these guys are doing things right and whether you can get the 4 orders of magnitude reduction in power that Wen Mei was talking about earlier this morning, that might be on the table if you think creatively enough. In order to do that, it just doesn't come out of nowhere, right? It comes out of having a very solid background in something. and so math, physics, those kinds of things are really that something. And as you go into take the AI into the physical world, there's it's going to be essential. So I think solid grounding while using AI as a tool and a friend, I think it's good. While recognizing it's really not your friend. That's an important thing to do, and taking the core courses and not egregiously using AI, those kinds of things. Again, these are temptations that are there. I see that in students, maybe not among the smartest ones, but save yourselves a little bit from the brain rot that could ensue if you do that. So. And the other part is, the other thing I wanted to say is that one of the benefits of being here is that you are a little shielded from the hype, the Silicon Valley hype. And that's, I think, important to be able to think differently. And I always sort of took that away from here, even though I went to Silicon Valley for some startups and things like that. But basically, there is a relentless hype that you cannot buy into if you really want to think for yourself and do something creative. And I think taking advantage of that fact that you are a bit shielded here, I think that's important too, and you should appreciate that as well. So.
I want to add to that, this luxury of considering fundamentals and being able to play around. I remember, actually, it was great to see Jin Zhao. I remember hosting him as I was on his thesis committee. I remember hosting him, and I remember making pictures at the board, of little squares. We were working on wideband systems. But, the fact that CSL was very okay with you're telling your student, go get a few colored pens and play with this, draw it. And I remember at one point, I had a student jointly with Sean Ma and Jen Yu Huang, who actually was one of, I think, the first hires at Marvell Semiconductors. He has done very well for himself. And he said, I feel a little silly. Like, I haven't done this since, middle school. And I said, just you have the equations, but play with it, draw it, try to intuit it. And when, he talked about this to Sean, Sean was like, oh, yeah, that's great. So there was this sort of a permission to just draw and try to understand things from scratch in your own way, and not necessarily a high pressure, as you said, there's a deadline for a conference next week, and, where's the draft? But more like, why don't you just try to understand it, play with it, try to feel it. I always was struck by that at CSL. That there was this sort of respect for that sort of playful intelligence, which in the end, I think, really is the approach that wins out. The really innovative, really groundbreaking things start from people going, I'm not going to assume this, or I'm not going to trying to make a delta or a little epsilon improvement. I'm really going to play with this and really try to figure it out for myself. In this very personal way.
And it doesn't stop you from going and, when somebody gives you a ton of money to make the self-driving work, you will do a great job of it because you have thought for yourselves.
Yeah, because you have a different approach to it, which is not the approach that other people will have, And that differentiator is so, and I think we've talked about, AI. I still call it machine learning. I mean, that differentiating yourself, not doing the same thing as everybody else becomes even more important in my sense.
I got to call it AI now. I mean, I was fighting it for the longest time. You got to.
I haven't given up, but give me another year.
No, it's get there.
Andy, your thoughts? Thank you, Muriel.
It's AI. That's my thought, yeah.
Oh, geez, Andy.
Yeah. No, we are all there.
We used to give longer answers.
As far as students go, the one thing I would say is if you have an opportunity to collaborate with multiple faculty at Illinois, do so. There's, it's unusual how well and how collegial how well the faculty get along and how collegial the environment is at Illinois. So it's really an opportunity for you to be able to, I think most of the people that you've heard talk, both in this session and other sessions, will tell you about the relationships with multiple Illinois faculty members, not just one. And that is truly unique. Madhow and I only overlapped at Illinois for like a year and a half, yet the one student that we collaborated with, she's, you know, an outstanding faculty member at George Mason University, an award-winning teacher and an associate dean. And, you know, that she did amazing work, but it was a great opportunity for me to get to work with Madhow and for her to get to work with both of us. And it was really an exciting time. And Ralph and I had a number of students that we collaborated together with and others. It really is a great way to get more, you know, more than your money's worth.
Thanks, Andy.
I can attest to that.
Thank you. So no questions from the audience still? Oh, there is one. Yes, please.
Panels here, and this question came up during lunch, and maybe it's a question for all the panels here. Many of you, you know, CSL alumni, if I call, went on to leadership roles in other places. You're coming back and talking about your fond memories of CSL. And I agree with all of what you're saying. And I'm wondering, I think this was addressed, if you have to replicate this environment elsewhere, what would be, you know, do you think it's feasible, or there is something special, maybe the JSEP, that gave the freedom for people to think without the pressure? So, you know, such opportunities don't exist anymore. What would be the building blocks to emulate or create an environment like this is one. The thought maybe is, you know, as Andy and Mark pointed out, there was no startups. Maybe that's a trick, because if you don't give startups, then faculty have to collaborate to get their initial funding. Might make you happy if that's the magic.
For me, this is an easy answer, because I had, you know, I mentioned earlier 2 of my teachers, you know, who I took so many classes from, but there were so many great teachers that I took classes from. The greatest researchers in their areas were also the greatest lecturers and professors in the classroom. Both Dave and Tom, my advisors, were incredibly good teachers in the classroom. Dilip Sarwati, I remember taking his, you know, digital math course, and he was just completely an engaged and wonderful instructor. And this is certainly affected me going forward. If anybody asks me what I do, I say I'm an educator. And I think that's because of my experience at Coordinated Science Laboratory, where that was the environment, that was the philosophy. Yeah, great researchers, but first and foremost, educators. Yeah, and that's why I'm sitting here on Zoom. Tomorrow morning at 8 a.m., I have to be in my classroom where my students are presenting, and I couldn't find a flight to pull this off. Otherwise, I would always want to be back in Champaign-Urbana for a visit. So that's what I think it is. It's an incredible educational environment because of the dedication and devotion of the professors who are also great teachers. You don't have these guys or gals who are just in their office writing high citation papers. They're in the classroom getting, you know, high citation marks from their students at the end of the semester.
Madhow, you want to add something? Madhow, you want to add something? No? Muriel?
I think it's really, really hard to try to pin down these intangibles. You know, I think one of the things that struck me here is it was very much an ethos, and that ethos, it was something that you were expected as a junior faculty to absorb and make your own. And certainly collaboration was one of them. I mean, we heard about the Wednesday lunches. so much happened there, from course assignments to, all sorts of decisions to talking about, maybe if a problem, a student was having a problem or so on. And so there was this sort of clear expectation that you were part of a collective and that there was this collective ethos. It was not explicit, but it was very strongly implicit and very strongly modeled. And I think it's because there were a few anchor senior faculty who just believed, still believe, and modeled it. I think that was it, and having those effectively anchor people is key.
So I could not set up a Wednesday lunch in Santa Barbara when I went there. It was impossible. So it's not easy to actually. So I have very close colleagues that I collaborate with with specific things, and we text each other and all that. But having that kind of thing, if it's not there already, it's hard to actually bring about at scale. Actually, it's hard work.
Andy, any comments?
So there's a couple of things. Illinois. One of the things that happened when I joined, and I hope it's still the case. You join as a faculty member, and you got an office whose door opens into the corridor where students can walk in, which is different from at a place like, well, I won't name the place, but a place where I was a grad student, where if you want to get to where a faculty member is, you have to go through an outer set of double doors where there's armed robots, and then there's an inner door where there's a dragon, and then there's three guards, and then you might make it past them to the private library, and then get stopped by the set of graduate students who are defending their advisor. So that silo and castle building was never really part of CSL or of Illinois. And even at places where you don't have big empires, if you have an institution where it's just tradition that, when someone is hired, they're given a lab. Here's your lab, right? Here's your office where you can hang the picture of your kids and you can put your thesis and textbooks. And here's your lab that's yours forever, right? This is your X thousand square feet or 100 square feet. Well, the problem with that is the natural tendency to want those number of square feet to grow over time and to never give them up and to never share them. And it's hard to undo that, after decades of people collecting lab space and equipment and things. The opportunity to share space and have graduate students interact with one another isn't there. And Illinois, we didn't have that. If you had a project that needed some space, you'd go to the CSL director and you'd say, I've got this project and, we got robots that are going to drive around the floor and send signals to each other. And they'd say, oh, well, Mindow's also got a project with some robots or, whatever. Maybe you could squeeze in with them in the basement or in that room. And if that project wound down and your students were no longer using it or making great use of it, and the CSL director said, someone else just got a big project and they need some space to do something fun. Can they squeeze in there too? And there was never an idea or a notion that this is mine and I can't share it. And that culture has been at CSL for a very long time. And it's hard to create that new at a place that it doesn't exist. So as a result, grad students from multiple research groups sit together in where they, plop down and do their studies, as well as where they take their measurements and build their circuits or whatever it is that they do. And that's hard to replicate, but I think it's important. It's really important to have sort of a communal living kind of view of research. It's unique.
Thank you, Andy. I think a question about signal processing and communication theory is due, because that's the name of this panel.
Oh, that.
So one concern that researchers, young and old, I guess, in this area have is, how do we stay relevant in this environment where everything is dominated by AI? And sometimes there are very scary questions. Where would I get a job? And I think that was brought up. If I do a PhD in signal processing or comm, versus, you know, me doing some AI and losing my identity and everything that I trained for many years. What do you see as a potential solution? How do we work around this problem? Because we cannot compete these days with big research labs like Google or Amazon or Facebook. We need to find our own niche, and I think Min did a great job presenting some ideas this morning that the executive committee collected. But what is your opinion specifically for these two areas in terms of where is our future, how do we stay relevant, and how do we not let these fundamentally important areas dwindle away because of AI? Al?
Yeah, sure. Well, what the big companies do with their teams of 50, they collect enormous amounts of data that we don't have access to.
We need
and then
volume.
they use, volume? Volume?
Just a second, volume. Oh, it's better. Please go ahead. Sorry for it.
Oh, can you hear me okay?
Yes. Mm-hmm.
Okay, good. So what these companies do with their teams of 50, with their enormous resources, is they gather immense amounts of data, which only they have, and they use their immense compute resources. But, you know, for the most part, that's what they're doing, is, you know, shoveling in data and so on. Yeah, their papers get hugely cited and so on because, well, everybody needs to use those models that they've built. But, you know, on the two ends, there's still a lot of theory that needs to be developed on understanding these models. It's very difficult to get in there, and I think only a very special few will be able to penetrate what really makes these models tick. And I think it'll almost require developing a kind of new language of representation for what these engines are doing, working with, you know, linguists and psychologists and so on. But on the other hand, you know, I had a colleague who passed away after winning the Nobel Prize at 100, and he said, you know, empiricists have very long careers, okay? And he was certainly that, and developer of the lithium-ion battery, which powers everything these days. And that, again, speaks to, you know, being a person who understands, you know, not just programming, but data collection, data, what kind of data is needed, and that sort of thing, because that is really the gold of today's, you know, I forget who said it, but data is today's oil or gold or something. And it's really the main resource. And yeah, we don't have the people data that Google has, but there's all kinds of other data that you can pursue your interest, you know, in some application direction and collect that data and make important contributions. And that is in the realm of communication and signal processing too. There's an awful lot of empirical work to be done in communications and the placement of antennas and the, you know, collecting actual data in the environment from antennas and so on. Ted Rappaport, you know, has pioneered that a little bit, but, you know, we need a lot more of that. And certainly in every branch of signal processing, there are examples of that too. So be a data scientist, not just a programmer, and then use the tools that are available that the big guys are producing, and you'll be valuable and you'll be hired.
Thank you.
I'm not super practical, so I think, well, so I'll give you a few things that I'm seeing, right? I'm seeing that so when this deep learning trend started, you know, it was just purely empirical and all just hyperparameter search and things like that. And then they started scaling, and when I look at the papers that are trying to scale, you see a lot of signal processing style ideas on coming up, like MUPI scaling and all that. And then I just see a couple of papers recently making a lot of noise on compression for the key value cache. So, and you know, people are learning signal processing on the fly in order to do that. Mechanistic interpretability on LLMs, you take something of the layer and then you learn a dictionary for that using lasso-like techniques, not lasso, something simpler than that, and try to interpret what the hell is going on in that layer, right? So, I mean, it's all pretty much signal processing. So if you aren't grounded in the fundamentals, at least in terms of coursework, I mean, if you're really smart, you'll pick it up on the fly, but there's nothing like that. So I think course-wise, you do need that. In terms of research, I think what Al was saying about data, beyond that, you can have, now that you have so much compute, you can have huge amounts of synthetic data, like NVIDIA, for example, talking of wireless, say NVIDIA, there's Shona ray tracing tools and things like that. So when you couple those things together with some strong intuition and strong fundamentals, you can do pretty interesting new things, actually, things that you couldn't do before. So, but again, without actually having the fundamental knowledge of the field and some sense of the field, it's hard to do it. It's exactly the same phenomenon, but actually at the research level, right? I was worried about brain rot at the high school and undergrad level, but you can also have brain rot at the research level if you don't have the background to actually exploit these powerful tools. So you either be enslaved by the tools or they are your tools, right? I mean, so I think that's the choice you have, right? So yeah, just cannot take the intellectually lazy way out here, or jump in desperation to, oh, what do I do to be employable, and take the sort of the zeroth order approximation to that. I think you have to think a bit further ahead, actually.
Thank you. Muriel?
Yes, so I'll cite Dave Forney, who was also a student of Bob Gallagher many generations before me, and he said, oh, in the end, the academics always win. And it goes back to, if you're doing something fundamental, you've got an ace up your sleeve, and, you really do. I mean, when we look at a lot of these systems and you're thinking about, what are some of the core challenges, how do you distribute these systems? How do you decentralize these systems? How do you acquire the data for these systems? That touches on all of the things we heard about: communications, networking, signal processing, coding, right? Those are necessary to make these things scale, not to apply them raw, but to actually make them scale. So I think that if anything, the scalability issues, and particularly scalability in a distributed and eventually decentralized way, those are actually gold mines for us, because that's what we know how to do. We really know how to do that. And you really have to think of these problems in a very axiomatic, clear, rigorous way, so that, you don't just get caught up in the difficulty and just try random patches here and there that, may help, but aren't going to solve the fundamentals. So I think that aspect around the fundamentals actually works very much to our advantage. Very much to the advantage of people with the kind of training that we have and the kind of training that CSL, provides its students, and that, going back to what we said before, it should be cherished because it is unique.
Thank you, Muriel. Andy?
I would say try and work on something that can't be done easily by, just running it out, just, running some latest model so that, a month from now, it will be, you might get it published in one of these conferences that are hard to get into only because you've got a bigger GPU than somebody else, but it'll be forgotten in 3 days when the next conference happens. The kinds of things that I think signal processing and communications and networking researchers are good at is taking a problem and mathematizing it in a way that you can capture its essence and think about it. Maybe you turn it into a toy that becomes differentiable or becomes embeddable in some space or some domain where there are properties that you can exploit. Those are the kinds of things that are so outside of the the realm of just asking Claude or ChatGPT to run a bigger version of it. I think that's what CSL is good at, and that's what our students are good at. One thing I remember, it actually involves one of Muriel's students. When we were looking to hire Todd Coleman, he had recently graduated from MIT and finished his thesis, and we interviewed him. We thought he was great, and everyone was excited about the work he was doing. And I remember we were so excited. Bruce read his thesis, and Bruce found an error in his thesis. Bruce said, "Oh, there's an error." And they talked about it, and they figured out how to fix it, and they were excited about where it was going. And MIT called up and said, "Oh, why are you guys interviewing Todd Coleman? We heard you found an error in his thesis." Like, yeah, and we're hiring him, and he's great. And then MIT said, "Oh, well wait a minute. We didn't know. Should we interview him? Maybe we should hire him." And then all of a sudden there was a scramble to try and get Todd Coleman. But it was because Illinois wasn't afraid to actually dig in and say, we can recognize good, excellent work. We know what the hard problems are, and we know people that can solve them. And I always thought that was the greatest thing. I was always proud of the fact that we would make an offer to a new candidate, and the next thing you know, Stanford and Berkeley and MIT were interviewing them because they said, well, if Illinois just made them an offer, they must be good.
Yeah, we are the gold standard for quality.
We truly are.
I said are. Thank you, Andy. I think this is the time to exercise democratic rights of the audience again. Any questions from the audience? Yes, please.
Yeah, given this AI and the whole scare about it, is there anything you're going to change?
Do I need a mic? Okay. So given all this AI, and I could sense the scare here, are you going to change anything in the way you maybe staff your research groups? Is the selection criteria at the input going to change?
No, I think it confirms the need to really think about fundamentals. If anything, it's made that need and that approach even more. It's gone from a preference to a necessity, in my view.
Yeah, I agree completely. Of course, given the funding uncertainty, it's unclear exactly how many you would recruit. And and it's true that you can do a lot more. A single grad student plus AI can do a lot more now. So that might change too. But I think the fundamentals have become even more important, as she's saying. Yeah.
And by the way, I should say, fundamentals do not preclude implementation at all.
Of course not. Yeah.
Oh, quite the contrary. As a matter of fact, you need to figure out the tougher fundamentals when you have an implementation in mind, right? Because if you don't have an implementation in mind and the problem's hard, you go, screw it, I'll get another one. But, when you go, no, actually, this is the problem, right? And you're going to have to think about it very hard, and you're going to have to use, colors and think about it until you get your head around it, because this is the problem.
And also code and use Cloud Code and do all that stuff too.
That's right. Yeah. But whatever it takes for you to explore. But I just wanted to highlight that. Yeah.
From my perspective, I mean, when machine learning, it was becoming obvious that it was so incredibly powerful, it was an easy thing to get into. Research-wise, naturally you could bring to bear these powerful models and so on. So, we used them. More importantly, I just continue to look for students who are bright and dedicated, who are visual thinkers. Being a visual thinker is very important in the space that I work in. For me, the greater impact, and just as in my work, has been in the classroom. So in the classroom, I had to, look at my image processing class and see dwindling numbers of students who are becoming less interested in the classical methods and so on, and wanted to learn machine learning for image processing. So at one point I had to slash my classes. I took a whole semester off from teaching so I could be a better teacher, and slashed half the material and brought to bear all this great machine learning stuff, which then attendance was up and it was a popular class. So changing in the classroom has really been as an academic where machine learning has been very dramatic in its impact for me.
Thanks, Andy.
It's a really exciting time. It's a lot of fun to sort of see how everything is changing, from how I take notes at meetings. Basically my notes at meetings are interactive discussions with Claude, because Claude is keeping my summaries together. Finish a Zoom meeting and you get an AI summary that you can integrate. The students are doing this in the classes, and if you're not changing the way that you think about exercising students' talents to leverage those tools, then it's a wasted opportunity. I think everything is changing. It's a really exciting time. Thinking back to the last time that sort of everything was in so much flux that I can remember was around the time that Muriel and I were graduating, and sort of this thing called the internet was just sort of making its way through academic circles, and people were wondering, what do we do with this and how do we engage with it? We didn't know then what to do with it, but a lot of really exciting and challenging research problems came out of it, and we changed the way we taught computer science and networking and all kinds of things, and it's a great time to be around.
So I must confess to being regressive. So I'm teaching a class called Machine Learning, a Signal Processing Perspective, actually. I created that class many years ago, and then I handed it off to a junior faculty for the last 4 years, and then teaching it again. Of course, I had to change everything. So my pitch there is use toy models to understand what's actually happening. So now I'm having to make up toy models for showing what a transformer does and things like that, right? So I just think, it's easy enough for them to, now that the coding barrier is gone, initially I used to have things, EC students came in without knowing PyTorch or Python, and it was a hassle for them. Now they can use Gen AI, they can use Gen AI for the homework, whatever. But the idea is for them to actually get insight through toy models, and also mandatory group exercises in every lecture, where they work together on something that I've just taught or something like that. So I think I'm very obsessive about the keeping on using your brain thing. Yeah.
That's great. Thank you all. So we're about 10 minutes away from concluding this panel. So if I may ask our panelists for final thoughts, 3 sentences, let's say, each. What is your favorite COM signal processing problem that you're looking at right now? Not right now, but this year, for example.
Trying to finally make augmented reality something that people will buy. And that will involve people putting on a pair of basically sunglass-sized things, kind of like the Facebook thing, Ray-Ban thing, in 2 different places in the world, and seeing each other in glorious high-resolution 3D, interacting with your environment, and so on. I think that's what'll do it. I don't think it'll be people like me that buy them. I think it'll be, if we can bring the prices down, it'll be the youth of America. Just like they made, teleconferencing between any 2 ordinary people popular with FaceTime.
Thank you, Al.
I guess 2 things. One is sort of using synthetic data, yet creating robust sort of AI solutions for some wireless problems, and then trying to use some communication theoretic ideas to create some novel architectures for in deep learning, both robustness and scalability. So.
Yeah, so 2 things. One is creating a universal data acceleration network for blockchain. I've mentioned the company Optimum that I've co-founded, based on networking and coding and network coding, really making the reality of a decentralized world computer that responds at the speed of a decentralized world computer true. And the other one is developing universal decoding algorithms. I've been working on that, something called GRAND, guessing random active noise decoding. and taking it from the information theory to the chips. So we've been doing the information theory and the chips. I think that's also very in line with a lot of what we heard today in terms of philosophy.
Thanks. Andy, final thoughts?
Sure. I've been having a lot of fun working in audio and acoustic problems for the last 10 years or so, both in air for in-room acoustics, augmented listening, making hearing and listening systems for people. I'm not only a signal processor, but I'm also a user. I'll tell you that since deep learning chips have made their way into the latest generation of hearing aids, if I go into a loud, crowded restaurant environment, I can hear human conversation better than anyone with normal human hearing. It's only getting better. And I'm really excited by the tools that we have available through deep learning to be able to learn complex environments and make adaptive signal processing even more adaptive.
Oh, that's great. So final call for questions from the audience, because we are 5 minutes away from a coffee break. Yeah. If not, it's always good to end on a really good high note. So thank you all for joining us, especially you all and Andy online and YouTube in person. Thank you.
And thanks to Olgica.
And I apologize for the many errors. I think I still was able to.
Error correction, we're really good
exactly.
at it.
I need to sprinkle them in. Thank you. Sorry.
Bye.
last session.
Last on the program, we probably have too many people.
I think since she left Illinois, I haven't seen her.
I see.
David, I did.
Dave.
Yeah.
It's more social. So he. Anyway, so it was surprised that he passed away.
Yeah, so I understand.
Even he was healthy.
Was healthy, but what? Was some
but
medical
then I
testing
think he went to medical check and found something. I think she had no symptom, but then that turns out to be cancer. I forgot what kind of cancer.
What happened?
Then I think he was in hospital, but he was in good spirit, and then maybe
I think,
he never felt too bad.
Where's Clara? She's the big boss.
Yeah, she's out there talking. Or maybe they operated. You go up there. Thanks. I think people are having oh, Andreas is here. It's back from Saudi Arabia.
Oh. Oh, Andres is here. Oh,
Yeah.
wow. That's what you mean. Oh.
Are you going to
So he
tell
was
me
asking
when you
about
want
you,
me to
whether you
start? Yeah, I'm not in a rush. You're still walking in. But you want me to start? All right. Good afternoon, everyone. This is the circuits panel. How's the volume?
Not good.
Not good. Okay, how's the volume?
See back there.
Not good. How's the volume?
Maybe it might as well.
No.
Hello, hello, hello? You'll adjust it. Okay.
I see.
So filler while he adjusts the volume. Welcome to the circuits panel. We good now? Okay. All right, I'm going to keep talking and hopefully you'll be able to hear. So I want to introduce our distinguished panelists one at a time, and I'm going to introduce them in chronological order based on their arrival date on the U of I campus. So we're starting with Tim Trick, who arrived on the U of I campus in 1965. In his time at the U of I, he served as CSL director, so it's very appropriate that he's here today, and as the ECE department head. In his career, he received many awards, including in 1984, the IEEE Centennial Medal. Now, I'm not going to read all of his awards because we'd be here all day, but I do want to mention one other award he received. In 1994, he received the Van Valkenburg Award from the IEEE Circuits and Systems Society. And I wanted to mention that award for two reasons. First, it's named after Mac Van Valkenburg, another one of our faculty members and former deans. Also, because another one of our panelists received the exact same IEEE award, and that's Steve Kang. So I think that was really cool. All right, next we have Ibrahim Hajj. He arrived on our campus in 1978. Like our other panelists, he received many awards in his career, including IEEE Fellow and AAAS Fellow. He left us in 2000 to become the dean at the American University in Beirut. But now he lives here again at least part of the year. I should have mentioned, Tim never left us, so he is our most loyal Illini. All right, Steve arrived on the U of I campus in 1985. During his career at the U of I, he served as the ECE department head. He left in 2001 to become dean at UC Santa Cruz, after which time he became the chancellor at UC Merced, and finally, president at KAIST in Korea. Like our other panelists, he's received many awards in his career, including the Van Valkenburg Award and the IEEE Millennium Award. Our baby at the end.
Not a baby.
Martin Wong.
So embarrassing.
He arrived as a professor on the U of I campus in 2002. It was not his first time on our campus because he earned his PhD at the U of I also earlier. I don't have the exact dates, but I think it was in the 1980s. Yes?
Yes.
Okay. All right. Sadly, he left Illinois in 2019, but that was to become dean at the Chinese University of Hong Kong. I should mention that during his time as an ECE faculty member, he served as the executive associate dean in the College of Engineering. After serving as dean at CUHK, he now is the provost at the Hong Kong Baptist University. Like the other panelists, many awards in his career. I will just mention he's received the Lifetime Achievement Award from the International Symposium on Physical Design. So with that, I'm ready to turn things over to our panelists. You'll learn about their expertise over the next hour and a half. I should mention they were all members of the circuits group at U of I. They have diverse research expertise and interests, but there is one theme that unites them all. They have all contributed to the field of electronic design automation, EDA. And with that, I'd like to turn the floor over to Tim, who I believe has a couple of slides to share.
Okay, thank you, Elyse. If I could have the first slide. As it was said, I came here in 1965. And I came because when I was at...
Stop. Can we pull up Tim Trick's slide deck, please?
Anyway, when I came here because when I was at Purdue doing my graduate research, if I ever, when I prepared for my exams, I always picked up Mac's book and read them. And they were very easy for graduate student read, and he was very, very famous electrical engineer. He was actually called the guru of electrical engineering because I had the opportunity of serving on an opportunity to choose the next dean of the College of Engineering back in '84, and there was Mac had a way of quizzing people in kind of a humorous way, and if he didn't like you, he would ask you some kind of questions that would kind of embarrass you. And so if you did that, the person would get to not like you. So there was a person on the committee that really didn't like Mac and didn't want him to be dean of engineering. And so I sat back and quietly and listened to it through the meetings. And finally, I called around, made a lot more phone calls around the country because Mac was known everywhere, even internationally, as a leader in engineering education. And in fact, John Winery said, how could you, and this was a distinguished professor at Berkeley, he says, how could you not choose Mac for dean? He's the guru of electrical engineering. That's how well known he was. And so in the final committee meeting, when this guy was spouting out how Mac should never be chosen, I made that comment to the committee and talked about all of his accomplishments and his fame, and the vote was all unanimous except for maybe one person. And so I was very proud of that moment to be able to have Mac to become our dean. But anyway, Mac also really built up the circuits and systems and computing area of the Coordinated Science Lab. That's when the lab dropped the classified research work, became unclassified, and brought graduate students in. Mac was associate director, and I think his job was really to build up circuit systems and computing area. And I remember he brought in Wat Maeda, Siddhan Huseshi, who was a graph theorist in circuit theory, Mac's area was in analog circuit synthesis. You might call it analog signal processing these days. And while Ed Jordan was away on sabbatical, he also served as the acting head of the department. And Mac used that as an opportunity to really load up faculty in the circuits and systems area. So he brought in Franco Preparata, Peter Kokotovich, Abe Haddad. I don't know if Ed Davidson was brought in at that time in computers, and he hired me in the nonlinear circuits area. So Mac had quite an influence in building up the circuit systems area, and he started the Allerton Conference on Circuits and Systems in, I think it was 1963, and as Vince Poor mentioned, the new assistant professors got to be the liquor chairman and run the bars at Allerton, and so I was always glad that the police never stopped me when my car trunk was loaded with cases of alcohol. But anyway, that was Mac's influence on that. Shortly after I got here, my thesis was on subharmonic oscillations in varactor circuits, because my advisor had got his PhD degree from MIT, and nonlinear circuits were really a big thing back in the 50s. But shortly after I got here, I thought, gee, the world's changing. The transistors having more and more importance in things. And when I was an undergraduate, my electronics course was vacuum tubes. And so I thought, well, maybe I should look elsewhere at things that I should do in research. And fortunately, I think it was Fred Orr from the antenna laboratory, where they had developed broadband log periodic antennas, said, I'm having a very difficult impedance matching problem, and especially over these broadband devices. You could do it for one frequency, but you couldn't optimize over broadband. So I thought about it and said, well, I'll develop a computer program to analyze microwave circuits, combine that with optimization methods, and then optimize over the performance over a broad band. So I did that for him, and we did some publications on that. And then I had another student that I was very lucky to have some students ask me some challenging problems. He was working over at Magnavox, that used to be over in Urbana, working on military radio circuits. And he says, I have to design these oscillator circuits. And of course, I'm breadboarding these in the lab. He said, I'd really like to simulate them. And he says, unfortunately, I don't have a lot of computer time. These integration methods are taking forever, and I don't know if they converge. So then I changed I said, okay, I'm teaching this course on nonlinear circuits and systems. I said, let's see if if the system is forced by a periodic input, there's going to be a unique state of the inductors and capacitors that if I can find that unique state, I just have to integrate for one cycle. And so it was a fixed point iteration problem. So we came up with a method for doing that, and it worked great. And he said, but gee, this doesn't solve my oscillator problem. I thought about it for a minute, and I said, oh, that's a limit cycle problem. So there is no one fixed state. But if I fix a point somewhere in that range, and I take the period as one of the unknowns, because he wanted to know the period of these oscillations, then I will be able to again do an iteration. And again, the method worked great, and we got a prize paper out of it, all because the student posed an interesting problem to me. But the world was changing very, very rapidly. And I thought, well, let's see, computer-aided design, circuit simulation. So I got really interested in using computers to solve circuit problems. So I got into developing more and more simulation techniques into my program, my courses on nonlinear circuit analysis and so forth. The other things that were happening was that digital signal processing, basically Mac went to Princeton to be department head in 1966 and left me to cover all these courses in analog circuits, in the nonlinear circuits and network synthesis and so forth. And so I thought the world is changing, and there was an opportunity that came up that there was a consortium, National Engineering Consortium in Chicago, that said digital signal processing is becoming very important. The telephone company, the telephone system is becoming digitized. And I thought, oh, so digital circuits. So Jim Kaiser, who's a Bell Labs guy who would come around and go up to Chicago periodically and give a short course on digital signal processing. So the National Engineering Consortium, I applied. They gave me a grant for tuition free to go to his 2-week course up in Chicago. Got all of his notes on signal processing. I said, that's what's going to go into the network synthesis course. So I started adding digital signal processing in that course. So here I was changing things to do more digital signal processing, doing computer-aided analysis. And I thought, okay, this is a lot of things to handle. So I went to a conference and met Ken Jenkins. Okay, Ken Jenkins is a digital signal processing guy. That's just who we need. I can kind of relieve some of my load, and he can do that. So I talked to Ken. He agreed to interview, and Ken Jenkins joined the faculty. Met Ibrahim Hajj, I think, a year or two later. He got his PhD degree from Berkeley, from Professor Koo. Yeah, was your advisor. Convinced him to come to the University of Illinois. And
the conference.
Yeah, at the conference.
Discuss.
Okay, and so anyway, I think in terms of our research that we were doing, I want to just sort of stop there because I want Ibrahim and the rest of the panel to say what happened from 1980 after that. But one thing that happened was that after being a head of Department of Electrical Engineering at Princeton, Mac came back to the University of Illinois. It surprised, I think, a lot of us that he really loved this university and coordinated science lab. So he came back to be part of our group. And he was named, he got the Granger Chair he was awarded the Granger Chair. And I think that was probably the first chaired professor position in the College of Engineering, maybe in the whole university, because we were a public university, and the myth was that, oh, the state, the taxpayers fund public education. They don't need our money. The private donors, they don't need our money. But David Granger wanted to honor his father, and he set up this chair, and Mac was named Dean of Engineering. So at that point, let's have the next slide. And about 1980, the semiconductor industry started losing market share drastically. Japan came out with memory chips that were cheaper and higher quality, and industry got very concerned about this, and they decided we need to do something about it. We need more engineers trained in semiconductors. We need more focused research. And so they put together, a consortium of companies put together the Semiconductor Research Corporation. And there was a lot of talk then about, most of us at that time were doing getting individual research grants and so forth. So there's a lot of talk about centers, and maybe we should have focus centers. And lo and behold, they named 2 centers in circuits. Carnegie Mellon, Steve Director was a Berkeley graduate, and the group at Berkeley was doing the SPICE simulation, and they were close with the semiconductor industry. But I was somewhat miffed. I don't know how Ibrahim felt, but I thought that, hey, we're doing some really good circuits work, and we got all these students out there in the Bay Area doing circuits research. We need a center. And if we don't get a center, that's in trouble. We're going to be in trouble because that's the direction that research is going. So I should point out that I did take a sabbatical at Berkeley in 73, 74. I took a year there because I wanted to learn more about integrated circuits, and that was the place to be. So I had a lot of contacts there, and I took all their notes, audited their courses in integrated circuits, and I came back and started courses at the University of Illinois in analog circuit design, digital circuits, and stuff like that. Well, in '83, I was due for another sabbatical, so I talked to my friends at Berkeley. They invited me to come back, and I wanted to see what was going on in their center. Berkeley was remodeling a wing of their building for microelectronics research. Stanford had put up a new microelectronics building. And I thought, we got to get rid of it. We got to get with it. So I took a sabbatical at Berkeley. January 1983, I've got my plane ticket, ready to get on the plane, and I get a telephone call. It was Bob Chen. And Bob said, I've got a serious medical problem. He wouldn't say what it was. I have to go in for treatment. He said, Tim, I talked to the advisory committee, and they want you. He didn't use the word acting director. It was like, the JCEP review is coming up in the fall. This is a very, very important review. We need someone to put it together. He wanted me to do that while he was on taking a leave. I thought, oh, I've got this plane ticket. I'm leaving. I even had a place rented in Berkeley. I said, I'm just going to have to travel back and forth. So I was doing that, traveling back and forth, getting ready for the JCEP meeting. And also we put together a proposal to SRC for what was very large-scale, reliable VLSI circuits and computing, Jacob. It was something like that. And for a center. And we heard back from SRC that, well, we've already got 2 centers in circuits, but we'll give you a $500,000 program. Well, that wasn't bad in those days. Berkeley had $1 million, we had $500,000. Let's see. And we did then, our JCEP funding came through, and we were safe for another 3 years. JCEP, as you heard, was the backbone, really, of CSL in those days. That allowed us to bring in young professors, to allow them some freedom to develop themselves and get their own grants and so forth. Now, the other thing is that NSF decided to get onto the bandwagon. They decided they were going to fund centers instead of individual grants. And I thought, here we go again. We were ranked University of Illinois Department of Electrical Engineering, and computer science was ranked pretty high, but we were ranked behind MIT, Stanford, and Berkeley. We were ranked number 4 in the nation. I thought, if we don't get an NSF, one of these NFS centers, again, our reputation could sink somewhat by not getting the center. So I asked Carl Hess, I said, Carl, we need to really put together an NSF proposal, and particularly the JCEP people were, even though they were going to give us 3 more years in funding at that time, they were kind of wondering and rethinking about how they should fund things. In particular, the Navy was funding our program, in particular the electronics division, and they really weren't into computers and stuff like that. They wanted the computer group in the Navy to fund that, and the computer group in the Navy said no, they weren't going to fund the JCEP program. So anyway, we knew all this was pretty touchy. So I said, Carl, let's put together a proposal. And Carl Hess put together a proposal that he called Physics to Function, because we had people in CSL that were doing materials research, and we had people doing communications, control, signal processing, computing, and so forth. So Carl put together a proposal for, again, it was a $1 million center they were setting up within NSL for a center. Unfortunately, NSF felt like that proposal wasn't focused enough, and they did not fund it. But Carl had put together this proposal, and lo and behold, Ted Brown's contact us and says, Ted Brown was in Vice Chancellor for Research. Ted says, I have a donor that's going to give $40 million for a new building. And he wants a proposal. He wants Carl Hess to chair a committee, and he wants Dave Walsh, who was in CSL, to chair a committee to put together a proposal. Turns out he was going to give it to Arnold Beckman to fund this proposal. Eventually, Carl had his act together because he had already put together one for NSF. Dave Walsh had a great difficulty trying to get South Campus to cooperate, so Ted Brown put them together in one committee and said, I want a multidisciplinary proposal across campus. So they put this proposal together. Now, Arnold Beckman then came to the university. All the press was there. Since a lot of our faculty, our CSL faculty, were part of that proposal, along with other departments and so forth around campus, I was invited, and I also was put on an advisory committee to set policy for this new research institute, because, I said I was going to use the CSL model as the way you fund the research institute. And so we're sitting there, press takes their photos and so forth, and then the press leaves. Then Arnold Beckman looks at Stan Eichenberry and he says, Stan, he says, now how long do you think it's going to take for you to get this building up? And Stan says, well, wow, this is a $40 million project. First, we have to get approval of the state to go forward with this. Then the state has to go out and get an architect, put it out for architecture firms to bid on this. And there's going to be some politics in what architectural firm is going to do this. And he says that then the architects, once we pick a firm, then the architects are going to have to talk with all of the faculty whose research is going to be in this. What kind of labs do they need? What kind of space do they need? And stuff like that. And then he says, after the architects get all of this mapped out, then the state has to go out for bid for contractors to do this work. And again, it's going to be a political process. So Arnold Beckman listens to all of this, and he says, Stan, I'm 85 years old. And he says, I want to be here for the ribbon cutting. And I could have this project done in 2 years. Stan just looked at him and said, I will do the best I can. So I'm going to come back to that story. Well, while all this is happening, we lose out on another NSF. Well, I'm trying to think who all funded it. The superconducting super collider. There's going to be a Argonne lab, Fermi Labs. That proposal, we didn't get that. The state of Illinois had put up $500 million for that facility, matching funds. We didn't get it because Vice President was from Texas, President George Bush. Texas got the grant, which was great because it was a colossal failure. But Thompson says, we got $500 million, we're going to put it towards science and technology research in the state of Illinois. Now, what's happening in the face of all of this, and I said seismic changes. Cedar Project gets funded for Dave Cook. The year after Carl Hess put in his NSF proposal, Greg Stillman puts in a proposal for electronics, for optoelectronics. That gets funded for $1 million. Larry Smarr puts in a proposal for a supercomputer center. That gets funded. So all of a sudden, Tony Graziano, who was the Associate Dean for Research Facilities, has to find space for all of these centers. And he says, well, we've got to tap into this $500 million. So he's going forward with the university administration. And my conditions were this. Back in '68, I was an office mate with Franco Preparato because we were crowded in the mechanical engineering lab at that time. But I think it was about '68 that we moved into the tower. The tower was finished. 67? Okay, good. You remember better than I. We moved into the tower. And at the time we did that, I was put on an EE committee because our faculty were going to be gone. Most of the faculty in CSL were EE. We were going to have to walk through the sledge through the rain and snow to get over to Everett Lab at Green and Wright Street. So I was put on a committee, and we were going to build an electrical engineering building at the southwest corner of Goodwin and Springfield, right across the street from CSL, so we could have a togetherness of our research activities. That never happened. There's the Vietnam War. Things were kind of tough during the 70s. So it never happened. But now I have another opportunity. I say, okay, Tony, we've got faculty that are going to go into the Beckman Institute from CSL. What's the future of CSL? What if we lose these people? How is this going to change? I said, and we got this microelectronics grant. So I said, first of all, I appointed a committee with, I had Bill Howard, who was the vice president of Motorola, to chair a committee for a new microelectronics lab to rival what Stanford had. And first, the university wanted to stick us at the southwest corner of Springfield and Wright Street, an old building there. Well, Bill Howard put together some people, and Bill from industry, and they came back and said, no way, if you want to really be competitive in microelectronics, we need a proper facility, proper clean rooms, and so forth. So I said, Tony, we got the microelectronics lab, we got the Beckman Institute up here, let's have a new ECE building over here, and let's put CSL over here, right? So we can have a big mall here of this research work. Tony says, well, Tony went to work on this, and he said, well, we've got to do something with Larry Smarr and Dave Cook. Well, Larry Smarr was going to be in the Beckman Institute, and he says, we'll put Dave Cook in this new building, and we'll put the CSL circuits and systems and computer people in the other half of this building, and we'll call the building Computer and Systems Research Lab. I think it was CSRL at that time. Okay. He said, so we'll do that. And we'll get, and he put forward these grants to the state, and of course, lo and behold, this is what we have here. Except we didn't get the ECE building because the higher administration and campus says, you guys got too much already. We got to halt things and do other things on campus. So anyway, those were fun times, but busy times, and this is where the master plan was put together for this quad here. Well, I'll just mention one other historical fact, because Pete Sauer's name was brought up, and he was working with the control group on power system problems, stability problems, and stuff like that. And when I became department head, Mac was the dean, and he was named the Granger chair, but he wasn't using the money. And I thought, you know, Granger gave this money for power engineering, and it's sitting there, and I can't report to Granger what great things we're doing. So I asked Mac, I said, is it all right if I let Pete Sauer use this money and challenge him to do something? And Mac said, sure. So Pete Sauer came back to me with the proposal to create a power engineering software lab. And what it was going to be a lab with about the Sun workstations had come out. And what were they? $5,000, something like that. Well, I had to deal with a revolt in CSL because Jacob Abraham, he wanted a $5,000 workstation, as I recall, along with the rest of the faculty. And they didn't want to pay the tax for the $1 million VAX machine sitting there in CSL. And that's what Pete Sauer wanted. He wanted Sun workstations in there and so forth. The whole camp, we're all moving to these workstations and doing away with these time-shared $1 million computers. That was a big, big change at that time. Anyway, Pete Sauer was great at being thankful for what things were happening, and he said, let's have an open house and bring David Granger down here. David Granger came with his chief engineer, Lee Flory, and they were blown away. They couldn't believe what these students were doing with these workstations, their research and their classroom projects. And Granger turns around and he said, if you had another $1 million, what would you do? And Pete said, well, I'll have to get back to you. And so Pete talked to, I don't know if Phil Krine's here. He was here earlier, but he said, I'll have to talk to Phil Krine. Anyway, talks to Phil Krine. He says, and he comes to me and he says, Tim, he says, Phil Krine wants to throw away all the old machines in the power engineering lab. And he wants to remodel that, and he wants these workstations with little motor generators, computers, all digitized equipment. He says, I can teach power electronics as well as we can teach the machinery. But he says, the faculty are dropping the courses in power engineering from the curriculum. They're no longer going to be required courses. And we need more students to be taking power engineering courses. This is before electric cars. Now there's no problem. But we need more. So he says, Tim, I want to give any student that enrolls in takes 2 courses in power engineering and does a project, I want to give them a $5,000 award. He says, that will be about $1 million. Phil Krein has costed out with our lab, our machine shop, what the cost is. I've costed it all out, and that's a little under $1 million. Which one should we give David Granger? And I hate to throw cold water on young faculty members. I really try to encourage them. So I said, let's just talk to David Granger, let him decide. And so David Granger invites us up. He gives us a tour of his facilities, which were really awesome, really state-of-the-art for a distribution center back in the 1980s. And then he sits us into a boardroom, and he says, I'm going to fund both. And then he says, but I want you to tell me about the Beckman Institute. Well, I had been involved in these committees and so forth, so I tell him how things have gone with Arnold Beckman and so forth. And then I tell him the story of what Arnold Beckman said to President Stan Eikenberry. Granger loved that story. I get back on campus, and within a few weeks or maybe a month or so, I get a call from our Associate Dean of Development in the College of Engineering. He says, Tim, you are not to ask Granger for any more money. He says, we have a big project in mind. And of course, that big project, well, first of all, we never asked Granger for any money. He's the one that came to us and was giving it to us. But anyway, that project was to get rid of all that old stuff, building, powerhouse, and so forth behind Engineering Hall, and to put in the Granger Engineering Library. And they need a statue of Pete Sauer out there, because Pete was like an adopted son to Granger and gave many more, he was great. So anyway, I felt like this was an opportunity for me to tell you about how this all developed up here. And it was really great. And in that period, in the late 80s and early 90s, every offer I made to an incoming candidate to a faculty position, they accepted it. They couldn't wait to come here. And it really had a big impact to see all the new buildings and the research facilities that were being developed here. It was really great. Okay, I took up way too much time.
That was fascinating, especially those of us who benefited. And with that, can we bring up the slides for Ibrahim Hajj?
Okay.
H-A-J-J. There we go. Whoop. Blinded! Help!
I feel like I am on the stage in Cranert. Well, before I talk about research and money, I want to share with you some personal memories and experiences at CSL, if I may. And then I talk about research a little bit. So for me, I consider CSL as a family. So I am very happy to be part of this family reunion to celebrate the 75th birthday of CSL. I built my career in CSL. And that's why when I left to become a dean at the American University of Beirut, we kept our house here, and even they allowed me to keep up my office in CSL, and I was coming here 3-4 times a year. Every time I come to the US, I travel a lot. And every summer we come here, so I never felt that we left. So when I finished my adventure there and retired, I came back here to have our center here. So we like the community very much, so we stay here, but we travel a lot. But I would like to thank Tim Trick for recruiting me here, because otherwise I wouldn't have applied, but he saw me at the conference.
I always wanted to get people smarter than I was.
And Tim and Tim recruited Steve Kang. But when he came for interview, I was in charge of the schedule. So at the end of the day, Mia, his wife, came along. Instead of taking them to a restaurant, I took them home, to our homes. And we chatted, you know. And Mia said, "How can you live here?" I said, "Why?" He said, "When we landed, everything around the city was smaller than in those days. Everything is brown." It was like these days, no greenery. "How can you live here?" I said, "Well, here the university is like a cruise ship, surrounded by an ocean of cornfields and soybeans. And on the cruise ship, you make friends with everybody. And you form a bond. So if you live here, you make friends, you bond. And if you go to the supermarket, you meet people you know. You go to the dentist, you people you know, the doctor, everywhere, Cranard, everywhere you go, you see people you know, which you don't have in a big city where you come from." And she accepted that. And she reminded me today that without you, we wouldn't have come, because she was not eager to come. And she was very happy to come here. Now, I want to claim credit with Dave Munson for recruiting Naresh Shambhak here. And the same thing, when Naresh came for interview, I took him home instead of a restaurant, and Leigh, his wife, was there, and I did the same trick on them. And they are very happy to be here, and Naresh is still here. So CSL is a great place to build a career. Lots of opportunity for collaborative research, as you heard since this morning. When I first joined U of I, CSL was in that building on Goodwin and Springfield. And my office was on the 4th floor. And next to my office was Peter Kokotovich. And next door was Mac van Valkenburg and Tim Trick and all these giants in their field. And it was very nice to become friends with them. And every noon at lunch, we used to have lunch together in a conference room on the 4th floor. And people, Tim Trick, Mac Valkenburg, Franco Preparata, Joe Cruz, Bill Perkins, Vince Poor, Mike Persley, Dave Monson, who else? Tamer Bashar, Michael Louis, lots of people. I may have missed some. Dilip Sarwati. We used to get together, have lunch, bring our sandwiches, and discuss very interesting topics about research, teaching, and especially administration, no politics. So it was very enlightening to be among all these people talking about these important topics, and you learn a lot. And every Thursday, we used to go out to have lunch in a restaurant. And Bill Perkins was the leader of that lunch. He would decide where to go. So it was a great family for me to be here, and I learned a lot. And what else I can tell you? Let me see my notes if I have any. So now I can say that my experience at CSL stays with me all my life. That's why I'm here. Now, research-wise, in the early 80s, when I came in 78, we were working on parallel computation for circuit simulation. So that parallel computing was coming up, and then we were trying to look at partitioning and how to use parallel computation to speed up simulation of large circuits. And then in the late 80s, we started working on power estimation. Power estimation was, power was starting to come up as a problem in VLSI design. I remember in 1990, IBM announced that they were able to fabricate a chip with 1 million transistors. So that was a big thing. And of course, now it is billions. So power was becoming a big issue. And Illinois was at the forefront in power design for low power. And we did some work, low power, from the circuit level all the way to the architecture level. And low power design is still a very active area of research in the circuit group at Illinois, in CSL. So I think industry caught up in low power design after we started this work here at Illinois. We also did some work in testing in collaboration with Janak Patel and Jacob Ibrahim, and we did lots of work in reliability of VLSI design and in noise analysis, and several of our students who graduated from the group went to Silicon Valley and started companies, and they were very successful companies, and they were bought by bigger companies like Cadence and Synopsys, and they became millionaires. So in that area, we could transfer what we did here at CSL to industry to have an impact. And all these tools, ADA tools that are used to design chips and to test them, etc., they contain software and methods and algorithms that were developed here at CSL. And without the atmosphere that CSL provides, the support, the collaboration, we would not have been able to do this. One thing I forgot to mention, to go back to my personal experience, is that the first year I was here, I was appointed the president of the liquor part at Allerton. So that was also a big accomplishment. So with that, I will...
Thank you, Ibrahim. That was great. Oh, Could we bring up the slides from Steve Kang?
Maybe later, yes. Let me talk first, and then,
well, we can still put the cover up.
Okay, yeah, you can. So, yes, I'm Steve Kang. Greatly enjoying the visit and deeply appreciate coming back and meeting old friends. I owe a great deal to CSL for my entire career, actually. So I like to give some episodes which may have had some impact for Illinois programs. So let me go back a little bit to my graduate student days. Back in early 1970s, I was a graduate student of Leon Chua at UC Berkeley. He's a Mac van Valkenburg's student at Illinois. So he was at the time a professor, and I became his research assistant. During that period, I met Professor Tim Trick. He was a visiting professor from Illinois, and I got to know him there first. Many years back, after graduation in 1975, I first worked at Rutgers University, the State University of New Jersey, as assistant professor for 2 years. And then joined the Bell Labs because I wanted to do something about the CMOS VLSI chip design. So I didn't know much about, but I was willing to learn and study day and night, chemical processing and different CAD tools and all that, because my thesis topic at Berkeley was a nonlinear circuit theory, highly theoretical. And there I learned about Ibrahim Hajj's work and also Tim Trick's work, earlier work on periodic systems simulation, convergence, all that. So I worked on it for several years. And at the end, I was made manager of a big project, Belmec 32, which became IEEE milestone last February, February 2025. And was a very memorable experience. But the AT&T at that time had trouble in manufacturing this chip, 32-bit CMOS microprocessor chip. So I led a manufacturing task force in Allentown, Western Electric, commuted there every single day from early in the morning, late at night. And we were able to manage production quite successfully. Then they said, you guys needed to be in Allentown, away from Murray Hill. So entire organization was going to move to Allentown. So I was one day sitting in Allentown plant office. Suddenly, bell rang, and it was a Tim Trick. Tim said, Steve, I hear that you are moving to Allentown. So since you are moving, why don't you move to Illinois? That was very memorable. So we came, and so Ibrahim said, when Mia said that there is no mountain, no river, we are not coming. But what Ibrahim said was quite poetic, actually. You are sailing together as a family in big ocean of a cornfield. So that convinced us to come, and the rest is history. But at Illinois, what I found in CSL and ECE department is a very excellent collegiality and also forgiving many mistakes. I made many mistakes, especially Tim Trick again. I was in charge one day to proctor PhD exam, but I was eager at that time to coach little kids' soccer games. So, my assignment was to proctor about 60 PhD students taking PhD exam. But I totally forgot it. And I was on the soccer field, coaching this soccer team and their matches. I didn't know until Monday. I came Monday, and the Fasang Rao, a junior faculty member, Steve, you didn't show up for PhD exam. Then I realized what a big mistake I made. What happened was they called Tim, and he came quietly to open the locker and then distribute the exam problems and proctor the exam. He didn't say anything to me, such a generous person. So I never forget. That was a great lesson to me. And then when I was in CSL, as the team said, we had the SRC program, JC program, which helped greatly. And one day, Tim came to me and said, Steve, we have a problem in SRC program. And what he said was, Professor C.T. Sa, world-renowned device physics professor, has SRC grant, but the industry doesn't know how to use his result. And probably didn't go very well for research review. So Tim said, I can give you one PhD student. What can you do? So I recruited Yusuf Leblebiti, who is now in Turkey as the president of Sabancı University. He came to me and says, looking for some topics. So I said, I don't know anything about hot carrier aging. That's the reliability that C.T. Sa was working on. But perhaps if we can create a computer model, transistor model, we can embed into SPICE-like a program and do some simulation. He did a wonderful job. We made a presentation to SRC. P.B. Gatet, director of TI Reliability Lab, complimented this. And then he said, you guys in universities do a good job, but they only want to work on clean problem, not dirty problems. So I said, what do you mean by that? And it turned out, he said, we have a problem in ESD, electrostatic discharge problem, what Elyse is an expert on. That time, Elyse was a PhD student at Berkeley. So he said, can you do something? So if you give some funding to support PhD students, we are willing to do that. So he said, no problem, we can give you support. So I got support and recruited Carlos Diaz, one of the distinguished alumni of ECE. Carlos came and he said he was debating either mixed signal processing or ESD, but I told Carlos, if you work on this one, nobody has worked on it that deeply, you can make impact. So Carlos agreed to be a PhD student. So I sent him to TI for 6 months to learn about their problem and the data, bring all the data, bring it back, and he developed a beautiful circuit model in VLSI-IO frame because it's difficult to detect because it's hidden in the substrate and not obvious. So we did something, developed the patterns, all that, and later on we found a big company, Intel, or that was Intel. They had a problem. They couldn't ship out the product because of the ESD problem. Among so many hundreds of I/O pads, they didn't know where the problem was. So as a last resort, they developed our tool, developed in our lab. They didn't have much the trust in it, but nevertheless, they had to because they didn't know what else they can do. And turned out exactly they could pinpoint where the failure was. They dissected the chip, and that was the problem. So they solved the problem. Product was delayed of several months because of that. But our pioneering work in ESD helped solve the problem. So because of that, SRC gave, it's a technical achievement award, excellent award. So that was the exercise we did because I trusted our students who did excellent work, and I never overruled them. I just trusted them, and they did a wonderful job. Then Tim later came again and said, Steve, we have a problem. So sort of he identified me as a problem solver. What happened was we had the Engineering Research Center, NSF Center, Center for Semiconductor Microelectronics, CSM. They had a problem. After first year review, it was a disaster. NSF wanted to take the center back. That time, it was a 10-year program. Every year they gave $2 million or $3 million. But they said, you guys at university just take money and do your own research without collaboration. And So they didn't like it. At that time, Nam So from MIT was an assistant director of NSF, and he threatened Illinois. So Tim came to me, so what can we do? So it was not popular among faculty members, especially device people. I said, maybe we can create a big test bed. So optical test bed to interconnect all the devices together and demonstrate that it indeed works. People, if your device research, you don't want that. Because what if your device doesn't work? Then they will finger point to you that it fails. But that was the only way that we could convince NSF that we can do it. And the rest is history. I was very fortunate to have John Lockwood, who is another distinguished alumnus, who has AlgoLogic in Silicon Valley. He has an FPGA company. He exercised FPGA to create an iPoint test bed, a pulsar-based, switch-based optical interconnect test bed. That architect was a computer science professor. So we did that, and then built a test bed to plug in laser diode, driver, the photo detector, all that, and demonstrate that indeed we can do optical transmission. That saved the NSF Research Center. And then we had also Navy Research Center and so on. So that forever gave me valuable lesson. Trust the student, encourage them to come up with some ideas. And in fact, one of my PhD students, who is now Cadence executive VP, he said, also Andrew Yang, who gave money to Illinois to create the Andrew Yang Award, he said, the best thing that my advisor did was give me total freedom. Even Andrew Yang, when we was working NSF Engineering Research Center, when you have a new device, you have to capture the behavior through modeling and then simulate in a new simulator. But embedding model idea and testing it, whether it works or not, takes forever. You have to decode several months. And then Andrew one day said, Professor, I have some idea. I can write the software to automatically put the code into a program like Spice. So we created the iSmile program. HP loved it. They gave many workstations even. So we did that. And then later Andrew became a good salesperson. I sent him to AT&T, Bell Labs, and everywhere. And they loved his idea. And he became University of Washington professor and then created his own company, startup. And now he's venture capitalist. But he said, best thing you did was give me total freedom. So that I learned also from my colleague in computer science, David Liu, C.L. Liu. He invited me to be on his PhD thesis committee, including Martin Wong here and then Jason Kang at UCLA. I watched him how he ran his lab in a group meeting. First statement in his group meeting is to his students, guys, what can you teach me today? That's an enormous demand, actually. Students must work very, very hard to teach their own professor who knows so much. But that was forever my lesson. And so as a result, we were able to achieve many, many good things. Also, Kim's former student, Ping Yang at the TI, he said, we have a problem, thermal problem. So we started doing electrothermal simulation and did some pioneering work for placing modules to even the temperature and so on. So that is sort of my research experience about looking back, including Bell Labs and CSL, Illinois, and my life in California, mainly as administrator. My golden period was in CSL. I thank Tim and Ibrahim Hajj and other colleagues who were lucky to recruit Elyse Rosenbaum, who is an experimentalist. So we were doing simulation, but Elyse really demonstrated how we can measure and characterize, improve all the design, and so on. So I'm immensely grateful. Yeah, thank you.
Thank you, Steve. Martin.
Finally. Well, thank you very much for the invitation. So give me the opportunity to be sitting up here. And congratulations for the 70th anniversary of CSL. Now, CSL is a very special laboratory. In fact, I think in University of Illinois, you have the MRL, we have the MNTL, now it's Nick Colonial MNTL, and we have CSL. All these are interdisciplinary research unit. They are pioneer in what they do. I'm now working in Asia. A lot of people are very interested now moving and doing more interdisciplinary research, saying that the departmental research are very in silo and we should do. And I offer my experience. I tell them how a real interdisciplinary research unit should look like. I mean, this is the real CSL. You have an independent director and everything, not just a virtual. A lot of times you see a virtual lab. So I'm very proud that I've been associated with CSL. But Elyse, I came here quite early. I may not look that old, but I arrived campus 1979, freshly graduated from University of Toronto. I was a math student. I was intended to do number theory. So at undergraduate, I already took 3 classes, and I was really want to get a PhD in majoring in number theory. And around that time is very strange. Everybody you meet, you want to move into computer science. Everybody. Now, not just my friends in physics, biology, geography, music. A lot of students just move. The barrier is very low. And you just have to take a few undergraduate classes in computer science. You'll be able to get a master. So, and then also during the orientation, the math department told us that while you are focusing on your math education, you should go and learn something in engineering, just to make sure that you'll get a job. Essentially, you didn't say that. So that's why a lot of people move into computer science. Was a new field. So I moved into computer science, but I have difficulty adjusting. So I passed my core in math. I got my master, and then I had 1 advisor, 2 advisors, 3 advisors. I worked with Bill Gear. I mean, world internationally renowned scholars in ODE, numerical analysis. And I worked with Ed Reingold. And then I finally worked with C.L. Liu. C.L. Liu, at that time, I think it was a time when, at that time called CAD, Computer-Aided Design, and now it's called EDA. It's actually at its infancy as an industry. So we're talking about early 1980s. So Dave Liu said he wanted to get into this field, and then I was one of the early students working with him in EDA. Now, let me tell you a little bit about EDA. Okay, so you are talking about 100 billion or more transistor packed into a chip of the size of a fingertip. 100 billion, and just the transistor. And then you have the interconnecting wire. And you're talking about, if you look at the whole world, the population is about 8 billion. You look at all the buildings, all the roads, and all these structures in the whole world. You string the whole thing into a size of a finger. It's not as complex as a chip that we are seeing today. So designing a chip is immensely a complex task. You need software. So that's actually electronic design automation. So that's and also when you have so many transistors and so many wires connecting them, where you put the transistor and how you connect them affect the size of the chip, affect the performance of the chip, affect the power consumption, affect the manufacturability and everything. So it's a very complex problem. So that's EDA. Now I work in this field at the time in the early 1980s. Now Illinois, particularly, I think a large number of faculty members excel in CSL, excel in EDA or CAP. There are 3 universities that I remember dominate the field, EDA, is Berkeley, CMU, and Illinois. Now, in Illinois, we had excel in testing. Of course, Professor Jacob Ibrahim. We have Janet Patel. And then we had Ken Fox, Prit Banerjee. They're both students of Jacob, and then they remain here as very productive faculty members. In fact, I met Prit Banerjee a few weeks ago in Germany. So he's doing quite well. He was CTO of ANSYS. His company was bought by Synopsys, and now he's a VP at Synopsys. So we talk about old days, Illinois old days. So he was very fond of fond memories of CSL. Circuit simulation, of course, all the greatest among the greatest are sitting here. Physical layout. Now, very interesting. Physical layout. Of course, I have to confess, I pretended to be like a CSL alumni, but I was not. My advisor was Dave Liu. CL Liu is in DCL, computer science. But at that time, Professor Franco Paparata was doing outstanding work in layout. Very theoretical work in layout, and then he had a number of good students working on the topic. The one that I'm most familiar with, work closely with, is Majid Sarasada. So he is now in UCLA. And of course, around that time also, we had Professor Jason Kang. Steve mentioned that. He's a superstar now in UCLA. For circuit simulation, I also know one of another. Of course, Andrew Yang was. I think at one point he was the richest investor in EDA in the country. Sachin Sapanekar. He is a superstar. He's Minnesota. He's a superstar in EDA today. I also met him recently. Also, we have high-level synthesis. Dan Geiske was here. And one of his students, Nikhil Dutt, is doing very well at Irvine. Illinois was a powerhouse. Both Dan Geiske was in computer science, both in ECE CSL and also in computer science. So that was the in 1980s. Now, Steve, I think Ibrahim mentioned something about the work that we did get transferred to companies easily. I'll tell you how that works. So if you look at there are 3 big companies today: Synopsys, Cadence, and Siemens. This Siemens EDA. Siemens EDA used to be called Mentor Graphics. It's got a purchase by Siemens. These 3 companies has the 90%, around 90% of the market share of the EDA. And Synopsys was founded in 1986, you see. We were working on EDA at a time when these big companies were not even founded. Cadence, 1988. Now, of course, Cadence is a merging of 2 companies, SDA and ECAT. But SDA and ECAT, they were founded between 1983 and 1988. So we're talking about around that time when I work on EDA, when we all work in EDA in CS. That was actually the EDA as an industry was still in infancy. Siemens EDA, previously Mentor Graphics, was I think was a little bit earlier, but it was a different kind of company. I think it will be 1981. I think so. That's and these 3 companies grew by buying companies. So a lot of people at that time create point tools because EDA is very complex. Even a layout problem break into like multiple steps. Each step is a software. They call point tool. A lot of people can, based on a point tool, you can form a startup. So a lot of people form a startup and get bought by one of these companies. These companies become bigger and bigger by buying some companies. And also, we publish. And they are very eager to see what university algorithm from university. And they will actually implement it in there. When I was a young assistant professor, I visited Cadence one time. And that was during ICCAD. And then I heard the manager saying that, did you go and get the proceeding back? You know, they're very, very eager to see what are the new things come out, and they immediately can implement this algorithm into their tools. So I was not surprised that you said, I mean, the technology was transfer easily, either with or without your notice. All right. So before I forget, Steve Kang recruited me here. And you know what? You know how he recruited me? One day, the bell rings. I pick up the phone. And Steve said, I heard that someone trying to recruit you. Why don't you come to work for Illinois? I guess you learned from Team Trick. So I found that it was a very effective strategy, so I've applied to recruit a few other faculty members. All right, so, another thing that I forgot to mention. I was a student here, and I had interaction with CSL, of course. Then we're talking about a CSL this morning, talks about the one on Springfield and Goodwin, right? I walk into the building, I tell you what, this is very superficial. I found that it's very upscale. I mean, today, if you walk in the building, you don't think that way. But at that time, you compare that with the rest of the other buildings on campus. I was a math student. Of course, alcohol is very beautiful. I mean, I like Gothic structure. But then the library is like a dungeon. You go down there, it's like all that. And then my first office was Elyse Hall. I mean, now, of course, now it's under renovation, or maybe already finished renovation. And I also in DCL. The CSL at that time, that building, was, to me, was like a 5-star hotel, to be honest. So, and then, of course, I was in Texas. A computer science department was in the building. There was an old building. Jacob, when you moved to ECE over there, I don't think that building was so pretty, right? So when I came back and looked at the CSL today, I also found that it's like a 5-star hotel. I like the exterior and everything. So, all right, so let me wrap up. I see the number 5 there. Okay, so I'll tell you that. You can see I started working on physical layout long time ago. I said, what's new? How come the problem has not been solved? Now, when I work on that, I didn't know any electrical engineering. My knowledge was only in math. So the problem at that time was purely a geometric problem. The circuit can be viewed as like a graph. I'm talking about embedding a graph on the plane, and then the routing, strongly a combinatorial optimization flavor. So it was a problem very suitable for someone with my background. Then when in the Texas, later on I moved to University of Texas at Austin. I stayed there for 15 years. And the problem kept changing. Now, yes, it's a graph embedding. Strictly speaking, it's not a graph, it's a hypergraph, and that's okay. You can always convert the hypergraph into a graph. But then, now if you're shrinking the feature size, the wire delay becomes significant. Suddenly, everybody has a timing kosher problem. Because you design this after the layout, and suddenly the delay, I mean, is not meeting your spec. So, and then when you move the transistor, you move the wire again. So you have no control on the timing. So that's why when you're doing the layout, you have to understand delay. So suddenly the problem, you have the electrical issue come into picture. And then also when you skip stringing the wire, then you cannot string in both dimensions because the resistance will be too high. So you end up you're stringing more on one side than the thickness. Then you like a wall. The wire is like a wall. And then you have parallel wires. It's like a lot of crosstalk signal interference. So now I have to worry about this when I'm doing the layout. Then, of course, power consumption is an issue. And then later on, manufacturability is an issue. And so because of the minimum feature size so small, the laser is the equipment you use is 193 nanometer. You're talking about making, at that time, 40 nanometer, 10 nanometer. So you have a lot of these short, otherwise you will not be able to print these wires. So you have to understand the manufacturability. So over the course of my entire career, the technology changes give me new problems. even though looks like it's the same old problem, but it's not. So I have a whole lot more to say, but I think I should stop here. Looking into the future, maybe I should say something about that. The shrinking is going to be more and more difficult. So that's why you really need to have the packaging. You need to, because now you're talking about 2 nanometer, going to be 1.8, 1.4, and so on and so forth. Eventually, you're not going to shrink so much. So now instead of increasing the density on a chip, you're going to package. So you're going to focus on the technology for making the package to be smaller, but then also they give you the EDA problems. Your layout, the wiring, and everything now is in 3D. Right? So, and also the problem becomes larger and larger. So acceleration by GPU, by FPGA, and so on. AI, definitely. AI is a big thing. AI, in the last 10 years, I don't think the technology for EDA has dramatically improved. So AI is something that might give you an edge over. So I think this morning Benoit was talking about Hong Kong has a lot of research money. So I actually work with my former CUHK colleagues. We got a grant about $10 million working on AI-driven EDA. So this is a 5-year project. Of course, we have quantum. Quantum is big. So quantum algorithm for EDA or EDA algorithm for making quantum chips. So these are the futures. Thank you very much.
All right, so Clara, who's our big boss here, we are officially at 5:30. Should we adjourn or should we do lightning round questions where it's like quick question, quick answer, quick question, quick answer? Your call, you're the boss. Correct. So you want to adjourn or questions? Okay, so I am going to invite the audience to grab these people at dinner tonight and ask all of your burning questions, because I know I have some. And let's thank them all again.